Hello and welcome to Sleepy Science. What if the universe is filled with objects so extreme that they seem impossible even when the physics is real? A city-sized star can outweigh the sun. A spoonful of its matter could weigh billions of tons. Black holes can spin near nature's ultimate limit, bend light into rings, slow time, tear stars apart, and collide hard enough to make space-time itself ripple. Entire planets can lose their atmospheres, rain molten rock, or drift through the galaxy without any star at all. And on the largest scales, most of the matter-shaping galaxies may be completely invisible, while space itself expands in ways that can carry parts of the universe forever beyond our reach. In this video, you'll explore 60 of the strangest real phenomena in modern astronomy, each one revealing just how far the universe can push matter, gravity, light, and time before your everyday intuition stops working. Before we begin, like the video and subscribe. Then settle in, because the deeper you look into the cosmos, the less ordinary reality begins to feel. A neutron star can pack more mass than the sun into a city-sized sphere. There are objects in the universe that make the word small almost meaningless, because a neutron star can contain more mass than the sun while measuring only about 20 kilometers across. If one were placed over a large city, the entire star could fit inside the metropolitan area, yet its mass could be greater than that of the star that lights our whole solar system. To understand how nature creates something this compact, you have to follow a massive star into its final moments. For most of its life, the star survives because gravity pulling inward is balanced by pressure generated deep inside. Eventually, the core runs out of fuel it can use efficiently, and that balance fails. The center collapses with extraordinary speed, forcing matter into conditions that ordinary atoms cannot tolerate. Electrons that once occupied large regions around atomic nuclei are driven into reactions with protons, helping create enormous numbers of neutrons. The core shrinks from something comparable to the size of a planet, or larger to an object no wider than a city, while retaining roughly a star's worth of mass. What stops the collapse is not ordinary gas pressure and not the heat of continuing fusion. At these densities, quantum effects and the behavior of nuclear matter resist further compression. That resistance can support the star, but only up to a point. If the remaining core is too massive, even neutron star matter cannot hold itself up, and the collapse continues toward a black hole. This places neutron stars in a remarkable middle ground, more compressed than white dwarfs, but not compressed enough to disappear behind an event horizon. Their gravity is so intense that the surface is nothing like the surface of Earth or even the Sun. Material there is bound with enormous force, and the escape speed can be a significant fraction of the speed of light. Even light leaving the surface loses energy climbing away from the star's gravity, allowing astronomers to learn about the object indirectly through the radiation that reaches us. Yet the deepest mystery is inside. Scientists know a great deal about the outer layers, but the exact state of matter in the central core is still being tested. Under those pressures, neutrons may interact in ways that cannot be reproduced in laboratories, and more exotic forms of matter may become possible. This is why measuring the mass and radius of neutron stars matters so much. Every precise measurement tells physicists something about how matter behaves when gravity pushes it almost to the edge of collapse. A neutron star is therefore not merely a dead star crushed into a smaller shape. It is a natural experiment in the limits of matter itself. You begin with an object small enough to cross by car in less than an hour, and end with something carrying more mass than the sun, forcing you to confront a strange truth. In the universe, size tells you almost nothing about how much reality can be packed inside. A teaspoon of neutron star matter would weigh billions of tons. A teaspoon is small enough to disappear into the palm of your hand, yet if that volume were somehow filled with matter from deep inside a neutron star and kept in the same compressed state, its mass could be comparable to billions of tons. The comparison is not meant to suggest that anyone could actually scoop neutron star material into a spoon and carry it home. It is a way of showing how extreme the density becomes when the empty structure of ordinary atoms has effectively been removed. Everyday matter feels solid, but it is surprisingly open at the atomic level. Most of an atom's size comes from the region occupied by its electrons, while the nucleus at the center is tiny by comparison. You cannot simply push normal atoms through one another because electromagnetic forces and quantum rules resist that compression. But inside a neutron star, gravity has already pushed matter far beyond the conditions found in ordinary solids, liquids, or gases. In much of the interior, the familiar separation between individual atoms no longer exists. Matter is packed at densities comparable to those found inside atomic nuclei themselves. That is why a volume small enough to fit in a kitchen spoon can represent an amount of mass that would be impossible to move, support, or even meaningfully handle on Earth. But there is an important scientific correction that keeps the comparison from becoming fantasy. Neutron star matter exists in that state because of the enormous pressure surrounding it. If you somehow removed a tiny sample from the star and placed it in ordinary conditions, it would not remain a neat, stable lump with its original density. The material would undergo violent changes as the pressure disappeared, and the exact outcome would depend on what part of the star the sample came from and what form the matter had there. So the famous teaspoon statement describes density under neutron star conditions, not a realistic object that could sit on a table. The density also changes with depth. The outer crust contains tightly packed nuclei and electrons, while deeper layers become increasingly dominated by neutrons, and the innermost core may contain states of matter that scientists have not yet identified with certainty. This means there is no single perfectly uniform substance called neutron star material. The star is layered, and the matter changes as pressure rises. What makes the teaspoon comparison valuable is that it gives your mind a way into a scale it was never built to understand. A mountain feels massive because it fills your horizon, but neutron star matter reverses that intuition. Enormous mass can hide inside almost no volume at all. You are used to judging weight by size, yet here the relationship breaks down completely. The spoon would look insignificant, but the amount of matter represented by that volume would belong to an entirely different physical regime. And once you understand why, the impressive number becomes less important than the lesson behind it. Ordinary matter is not as compact as matter can possibly become, and under enough pressure, nature can erase the spacious architecture of atoms and replace it with something so dense that your everyday sense of weight no longer has any useful scale. Some black holes spin at nearly the speed limit of the universe. You might expect the darkest objects in the universe to sit silently in space, but some black holes are doing something far stranger. They are rotating as close as nature allows to an ultimate cosmic limit. This does not mean a solid black surface is literally sweeping around like the edge of a wheel, because a black hole has no ordinary surface at all. Instead, scientists describe its spin by how rapidly the black hole's gravitational structure rotates. And observations show that some appear to be remarkably close to the maximum rotation permitted by Einstein's theory of gravity. The reason begins before the black hole even exists. A star is already rotating when its core collapses, and as that enormous amount of material contracts into an unimaginably smaller region, its rotation can become much faster, rather like a spinning skater accelerating when pulling their arms inward. A black hole can also gain additional spin over time by swallowing matter that repeatedly falls in from the same general direction, or by merging with other compact objects. But once the rotation becomes extreme, something happens that has no familiar equivalent on Earth. The black hole begins dragging the surrounding space-time around with it. If you could somehow hover close enough to such an object, you would discover that remaining completely motionless relative to the distant stars could become impossible. Space itself is being carried around the black hole's rotation, forcing everything nearby to participate to some degree. Matter orbiting in the same direction can travel closer to the black hole than it could around a non-rotating one, and astronomers can study the intense radiation produced by this rapidly moving material to estimate how fast the hidden black hole is spinning. Rotation can even store an enormous amount of usable energy, and some theories of powerful cosmic activity rely on extracting energy from the environment of a spinning black hole. Yet there is a limit. A black hole cannot simply be spun faster and faster without consequence. Relativity places a maximum on how much rotation it can possess for its mass. So when astronomers say that a black hole is spinning near the universe's speed limit, what they are really describing is something more subtle than a fast-moving object. They are describing gravity pushed into a regime where rotation changes the behavior of space around it. You begin with the familiar idea of something turning, and you end somewhere much stranger, a place where the object is not merely spinning inside the universe, but compelling the geometry of the universe nearby to turn with it. Time can pass more slowly near a black hole. Imagine returning from a journey and discovering that the people who stayed behind have aged more than you have, even though every second of your trip felt completely normal. Near a black hole, that is not a fantasy about a broken clock. It is a real consequence of how gravity affects time. Einstein's theory of relativity tells us that time does not pass at one identical rate everywhere in the universe. Stronger gravity changes the rate at which time passes when compared with regions where gravity is weaker, and because a black hole creates an extraordinarily intense gravitational environment, the difference can become dramatic. If you traveled close to one while another person remained safely far away, your own watch would continue ticking normally from your perspective. Your heartbeat would feel ordinary. Your thoughts would not suddenly become slow, and you would have no sensation that time itself had changed. The surprise would appear only when your clock was compared with the clock of the distant observer. Less time could have passed for you than for them. This phenomenon is called gravitational time dilation, and the important point is that it is not unique to black holes. Even Earth slightly affects the rate of time. Extremely precise clocks placed at different heights can accumulate tiny differences because they experience slightly different gravitational conditions. A black hole simply pushes the same principle into a far more extreme regime. Now consider what a distant observer would see if you continued approaching the boundary beyond which escape becomes impossible. The light carrying images of you would have to climb outward through increasingly strong gravity. Those signals would arrive progressively more delayed and shifted toward longer wavelengths, making your motion appear slower and your image dimmer. From far away, you would seem to approach the boundary more and more slowly, eventually fading from view. But this is where intuition can mislead you. You would not personally feel yourself freezing. According to your own clock, time would continue. And under the idealized conditions used in relativity, you could cross that boundary after a finite amount of your own time. Two observers can therefore describe the same journey differently, without either one being wrong, because there is no master clock outside the universe, forcing every location to share one universal present. That may be the deepest thing a black hole teaches you about time. You grow up imagining seconds as identical containers handed equally to everyone, as though the entire cosmos was synchronized to one invisible ticking clock. Physics reveals something less comfortable and far more interesting. How much time passes depends partly on the path you take through the gravitational landscape. Time is not merely what happens while the universe changes. It is woven into the structure that gravity itself can shape. And once you understand that, the question, how much time has passed, quietly stops having one universal answer. Two black holes can collide and shake the fabric of space-time. For more than 1 billion years, a message can travel across the universe without using light, sound, or any particle you could catch in a telescope, and its source may be two black holes falling into each other. When two black holes become bound by gravity, they can circle one another for an extraordinarily long time, but their orbit slowly changes because the system loses energy through gravitational waves. These waves are not vibrations moving through some invisible substance. They are tiny distortions in space-time itself. As energy escapes, the black holes draw closer together, their orbits become faster, and the process accelerates until the final moments happen with almost unimaginable violence. Instead of two solid surfaces crashing, two regions of extreme gravity merge into one larger black hole, and a portion of the system's mass is converted into energy carried away by gravitational waves. During the strongest part of such a merger, the power released can briefly exceed the combined light output of vast numbers of stars. Yet the event may produce little or no visible light at all if there is no surrounding matter to glow. This is why these collisions remained hidden for so long. Astronomers were accustomed to learning about the universe by collecting light, but gravitational waves opened an entirely different way of observing it. When one of these waves reaches Earth, it stretches space in one direction while squeezing it in another by an almost impossibly small amount. You would never feel this change in your body, yet instruments built with long laser paths can measure distortions far smaller than the width of an atomic nucleus. From the pattern of the signal, researchers can work backward and learn how massive the original black holes were, how quickly they orbited, how far away the merger occurred, and what kind of object remained afterward. The final signal rises in pitch as the orbit speeds up, then fades as the new black hole settles into a stable state. What you are hearing when scientists convert that signal into sound is not the actual noise of a cosmic collision traveling through space. It is a translation of changing spacetime into frequencies your ears can recognize. That distinction matters because the discovery tells you something deeper than the fact that black holes can collide. Space is not merely an empty distance separating objects. It has a geometry that can bend, stretch, and carry information about violent events across billions of light years. A merger that happened long before humans existed can alter the distances between mirrors on Earth by a fraction smaller than an atom. And from that nearly invisible motion, you can reconstruct the final seconds of two objects that emitted no light you ever needed to see. The universe, in other words, does not only reveal itself by shining. Sometimes it whispers through the shape of space itself. A magnetar can have a magnetic field, trillions of times stronger than Earth's. Compass needle is enough to remind you that Earth has a magnetic field, but near a magnetar that familiar force becomes so extreme that the word magnetism almost feels too gentle for what is happening. A magnetar is a rare type of collapsed star whose magnetic field can be hundreds of billions or even trillions of times stronger than Earth's, making it one of the most magnetically intense objects known. The star itself is small on a cosmic scale, but the field around it can dominate the behavior of matter and radiation across enormous distances. To understand why this is so unusual, think about what magnetic fields normally do around you. They guide compass needles, help motors turn, move charged particles, and influence electrical currents. Near a magnetar, those same basic physical rules are pushed into a regime that cannot be recreated on Earth. Charged particles are forced to move along magnetic field lines. The surrounding environment becomes flooded with high-energy radiation, and even the star's rigid outer crust can be placed under enormous magnetic stress. Over time, the field can twist and rearrange, storing energy much as a bent object stores mechanical tension. When that stress becomes too great, parts of the crust may crack or shift suddenly, and the magnetic field can reorganize in a violent event that releases intense bursts of X-rays and gamma rays. Some of these eruptions last only fractions of a second, while rare giant flares can release an extraordinary amount of energy almost instantly. One such flare from a magnetar thousands of light years away was powerful enough for its radiation to disturb the upper layers of Earth's atmosphere, even though the source was nowhere near our solar system. Yet the magnetar does not spend its entire existence exploding. Between outbursts, astronomers can watch its rotation gradually slow, measure changes in its radiation, and use those changes to estimate the strength and structure of the magnetic field that cannot be seen directly. That field also helps explain why magnetars behave differently from many other dead stars. Much of their observable activity appears to be powered not mainly by ongoing nuclear reactions, which have already ended, but by the decay and rearrangement of their magnetic energy. Scientists are still investigating exactly how such enormous fields are created during the star's birth and how their internal structures evolve afterward, which means magnetars are not merely spectacular objects but laboratories for physics, under conditions unavailable anywhere on Earth. And this is what makes them worth thinking about long after the dramatic numbers fade. You never actually see a magnetic field with your eyes. You see what it forces matter to do, how it redirects particles, how it heats regions of a star, and how it releases energy when its structure changes. A magnetar therefore teaches you something quietly unsettling about nature. Some of the most powerful things in the universe are completely invisible, and you know they exist only because everything around them is forced to obey. A star can collapse into a black hole without producing a normal supernova. A massive star can die so quietly that astronomers discover its death not by seeing something appear, but by realizing that something familiar has simply vanished. You may have learned the usual story of a very massive star ending its life in a spectacular supernova, throwing its outer layers into space while the central region collapses. But nature does not guarantee that every dying star gets such a dramatic ending. A supernova explosion has to accomplish something surprisingly difficult. Material that has begun falling inward must somehow receive enough energy to reverse direction and escape the star's enormous gravitational pull. During collapse, a shock forms deep inside the star, but that shock can lose energy and stall. In many successful supernovae, processes involving the tremendous flood of neutrinos produced in the collapsing interior appear to help revive the shock, allowing it to move outward and tear the star apart. But in some sufficiently massive stars, the situation may turn against the explosion. The central region can continue gaining mass. The shock may never become powerful enough to expel most of the star, and material that briefly moves outward can fall back again. Instead of the entire outer star being launched into space, much of it may ultimately disappear inward as a black hole forms. This is often called a failed supernova, although failed can be misleading because the star does not necessarily become perfectly dark in a single instant. It may briefly brighten, shed some of its outer material, glow in infrared light, or produce a much weaker transient than the brilliant supernova you might expect. Astronomers have even monitored a massive star in another galaxy that became brighter for a period and then faded until the original star could no longer be seen, making it one of the strongest observational candidates for this kind of quiet black hole birth. The evidence is compelling, but scientists remain careful, because proving that a distant vanished star has become a black hole is much harder than simply watching it disappear. That uncertainty is part of what makes these events scientifically valuable. If a significant fraction of massive stars collapse this way, then astronomers may have underestimated how many black holes are born without announcing themselves through bright explosions. It would also change how you think about what dying stars return to their galaxies. A successful supernova scatters newly created elements outward, mixing stellar material into the gas from which future stars and planets can form. A failed explosion can keep more of that material trapped in the collapse instead. So the difference between a loud death and a quiet one can influence not only the remnant left behind, but the chemical history of the surrounding galaxy. And there is something strangely humbling about finding such an ending in a universe we often associate with spectacular destruction. The birth of a black hole does not always require a cosmic firework visible across millions of light years. Sometimes gravity wins with surprisingly little ceremony, and a star that once occupied a clear point in the sky simply stops being a star you can see, leaving astronomers to infer its final transformation from an absence where light used to be. Some stars are thrown across the galaxy at millions of miles per hour. A star does not need an engine to become one of the fastest travelers in the galaxy. Under the right circumstances, gravity itself can turn a perfectly ordinary star into a projectile, moving at millions of miles per hour. Most stars spend their lives following relatively orderly paths through their galaxies. held within the collective gravity of billions of other stars, gas clouds, and unseen matter. But a small number are found moving so quickly that the galaxy may eventually lose them altogether. These are often called hypervelocity stars, and one of the most remarkable ways to create one begins with two stars that are already orbiting each other. If such a pair wanders dangerously close to the enormous black hole at the center of a galaxy, the difference in gravitational pull across the binary can become strong enough to tear the pair apart. One star may be captured onto a tight orbit around the center, while the other receives an extraordinary gravitational boost and is flung outward. No explosion has to push it, and no mysterious new force is required. Energy that once belonged to the motion of the binary system is redistributed during the encounter, leaving one star more tightly bound and the other racing away with far more speed than it had before. Astronomers have found a particularly convincing example whose motion can be traced. Backward toward the center of the Milky Way, it is currently moving through the galaxy at roughly 1,755 kilometers per second, close to 4 million miles per hour, and its reconstructed path indicates that it was launched from the galactic center about 5 million years ago. At that speed, a star could cover roughly the distance between Earth and the Sun in about a day. Yet even such an astonishing journey still takes millions of years when the destination is measured on the scale of a galaxy. The central black hole is not the only possible accelerator. In some binary systems, one star can explode and suddenly remove much of the gravitational bond holding the pair together, allowing its companion to fly away with the orbital speed it already possessed. In crowded star clusters, close encounters involving several stars can also exchange enormous amounts of orbital energy and eject one participant at high velocity. This means that a runaway star can carry a record of the violent environment that launched it. Astronomers can measure its direction, speed, age, and composition, then work backward like investigators reconstructing an ancient accident. Some fast stars remain gravitationally bound and eventually curve back through the galaxy, while the fastest can exceed the local escape speed and continue outward into the galactic halo, potentially becoming solitary travelers through intergalactic space. That makes them useful for more than setting speed records. Their trajectories can help scientists study the Milky Way's gravitational field, because the path of a star moving through the galaxy responds to mass you can see, as well as mass you cannot. And perhaps the strangest part is that the star itself may remain almost ordinary throughout the experience. It can continue shining and aging, much as it did before, unaware in any physical sense that its entire cosmic future has changed. One gravitational encounter can transform a star that once belonged to a familiar stellar system into a traveler that may never return, reminding you that in a universe ruled by gravity, even something as enormous as a star can sometimes be thrown away like a stone. A black hole can tear a star apart before swallowing it. A star can come close enough to a black hole to die without ever reaching the point of no return. The reason is not simply that the black hole pulls hard, but that its gravity can pull very differently on opposite sides of the same star. If a star passes sufficiently close, the side facing the black hole feels a much stronger attraction than the side farther away, creating what astronomers call tidal forces. Stars normally survive these differences because their own gravity holds their material together. But there is a distance at which that internal grip can lose the contest. The star begins to stretch, first subtly and then catastrophically, until its gas is pulled into a long stream and the original spherical star is destroyed. This event is known as a tidal disruption, and it reveals something counterintuitive about black holes. They do not always swallow objects whole. In many cases, the destruction happens outside the event horizon, where the torn stellar material can still remain visible to the rest of the universe. Roughly speaking, part of the debris may be thrown onto trajectories that carry it away, while another portion remains gravitationally bound and eventually falls back toward the black hole. That returning material does not simply vanish immediately. Streams of gas can collide with themselves, heat dramatically, and begin forming a rapidly evolving disk around the black hole. For weeks, months or sometimes longer, the system may brighten enormously in ultraviolet light, X-rays, visible light, or other wavelengths, allowing astronomers to watch the aftermath of a star being dismantled from galaxies millions or even billions of light-years away. These flares are especially valuable because many enormous black holes spend most of their lives in a quiet state, with little surrounding material to make them obvious. A wandering star can briefly illuminate one of these otherwise hidden objects, almost like throwing dust into an invisible current and suddenly seeing the current's shape. Not every encounter ends the same way. A star that passes slightly farther out may lose only part of its outer layers and survive to return on another orbit, potentially suffering repeated stripping. A deeper encounter can destroy it completely. And strangely, the most massive black holes are not always the best at producing a visible event. If the black hole is enormous enough, a sun-like star may cross the event horizon before tidal forces tear it apart outside, leaving far less of a luminous warning for distant observers. So the spectacular destruction you see depends on a delicate relationship between the size of the star, the mass of the black hole, and how close the encounter becomes. What begins as a simple idea of a star falling into a black hole therefore unfolds into something much richer. Before anything is swallowed, gravity can separate a star into streams, scatter part of its substance back into space, heat the returning material until it shines across a galaxy, and give astronomers a temporary laboratory for studying an object that was previously almost invisible. The star is lost, but in being destroyed, it can reveal the very thing that destroyed it, leaving you with an unsettling inversion. Sometimes the clearest evidence of a black hole appears not when it consumes light, but when a star gets close enough to make the darkness briefly shine. A dead star can spin hundreds of times every second. There are dead stars in the Milky Way that complete an entire rotation in less time than it takes you to blink once, and some turn hundreds of times during a single second. These objects are neutron stars, but the fastest members of the family usually have a history very different from a newly formed stellar remnant. A young neutron star can already rotate quickly, yet over time its magnetic field and the particles it sends into space tend to carry rotational energy away, gradually slowing it down. So how does an old stellar corpse end up spinning faster again? The answer can begin with a companion star. If the neutron star belongs to a binary system, its companion may eventually expand or lose gas, and some of that material can spiral toward the neutron star. The falling gas carries angular momentum with it, meaning it does more than add mass. Over very long periods, it can push the neutron star around in the direction of the flow, steadily increasing its rotation rate. Astronomers call this process recycling, because a neutron star that had been slowing for millions or billions of years can effectively be spun back up into an extraordinarily rapid rotator. The result can be a millisecond pulsar, named because one complete turn may take only a few thousandths of a second. The fastest confirmed examples rotate more than 700 times each second. That number becomes easier to appreciate when you remember that a neutron star is still many kilometers across. Material near its equator is therefore sweeping around at a significant fraction of the speed of light, yet the star remains intact. It cannot spin arbitrarily fast, however. Increase the rotation enough, and eventually the outward tendency at the equator would compete too strongly with the star's gravity. So there is a physical breakup limit beyond which a stable neutron star should not survive. The exact limit depends on what the star is made of internally, which means finding extremely fast rotators can actually help researchers test models of matter under conditions that cannot be recreated on Earth. The rotation also gives astronomers a way to notice these objects across enormous distances. A neutron star can produce beams of radiation connected to regions around its magnetic poles. If those beams are not perfectly aligned with the rotation axis, they sweep across space as the star turns. When one of them repeatedly crosses Earth, a telescope detects a pulse, then another, creating the famous lighthouse effect. Nothing is physically switching on and off hundreds of times each second. The beam is simply passing across our line of sight again and again as the star rotates. And this is where the object becomes more than a cosmic curiosity. An ordinary star may change slowly enough that a human lifetime reveals only a fraction of its evolution. But a millisecond pulsar exposes its motion continuously, allowing astronomers to count billions of rotations and detect minute changes in how that motion evolves. Beneath that rapid rhythm lies a surprisingly long story. A massive star lived, died, became a compact remnant, gradually lost rotational energy, then in some cases borrowed angular momentum from another star and began spinning at an almost absurd rate again. The star is dead in the sense that its original nuclear burning life has ended, yet it can become one of the most dynamically active clocks of motion in the sky. Perhaps that is what makes these objects so compelling. Stellar death does not always lead towards stillness. Under the right circumstances, a star can lose nearly everything that once made it recognizable and end up rotating faster than it ever did while it was alive. Some pulsars are more precise than the best atomic clocks. There are stars so regular that astronomers can predict the arrival of their pulses years into the future, and notice when they are late by an amount far smaller than a heartbeat. But calling them simply better clocks than every atomic clock hides the more interesting truth. Certain millisecond pulsars are among the most stable natural timekeepers ever discovered, especially when their behavior is averaged over very long periods. Although the finest laboratory atomic clocks can surpass them in short-term precision, what makes pulsars remarkable is that their timing comes from an object thousands of light years away rather than from carefully controlled equipment on Earth. Each pulse arrives because a rotating neutron star sends radiation across our line of sight again and again. And once astronomers build a model of its rotation, they can predict those arrivals with astonishing accuracy. Yet the pulses are not perfectly spaced at the telescope, because the signal has to travel through a moving universe. Earth circles the Sun, the pulsar may be moving through the galaxy. Interstellar electrons can delay different radio frequencies by slightly different amounts. And some pulsars orbit companion stars, whose gravity continually changes the distance their signals must travel. Researchers correct for these effects so carefully that what remains becomes a record of the pulsar's underlying rotation. That is when tiny irregularities become scientifically valuable rather than annoying. A sudden small change can reveal a disturbance inside the star. A repeating shift can betray the gravitational influence of an unseen companion. By monitoring many exceptionally stable pulsars spread across the sky, astronomers can even search for extremely long gravitational waves passing through our region of the galaxy, because those waves would alter the arrival times of different pulsars in a correlated pattern. This turns an entire collection of dead stars into something resembling a galaxy-sized detector, with Earth sitting at one end of every timing baseline. Pulsars have also been used to test theories of gravity and to measure the masses and orbital behavior of compact objects with extraordinary precision. Their usefulness comes not from being magically perfect, because they are not. Some slowly lose rotational energy, some suddenly change their spin, and many are far too irregular for precision timing. The extraordinary ones are valuable precisely because astronomers understand those imperfections well enough to separate predictable behavior from genuine surprises. And that is a more powerful idea than the popular claim that a pulsar simply beats an atomic clock. A clock tells you when something happened. A precisely timed pulsar can tell you that something along thousands of light years of space has changed. By listening to a rhythm produced by a star you will never visit, you can measure motion, gravity, invisible companions, and disturbances in the structure of the universe itself. What appears at first to be repetition becomes information, and the closer you listen, the more you realize that perfect regularity is not the goal. The tiny departures from regularity are where the universe begins to speak. A black hole can be surrounded by matter hotter than most stars. The black hole itself may be dark, but the material dying around it can become one of the brightest and hottest things in its entire neighborhood. Gas approaching a black hole rarely falls straight inward in a clean vertical plunge. because it almost always carries some sideways motion. As a result, it begins orbiting and spreads into a flattened structure known as an accretion disk. When neighboring layers of material move at different speeds, the closer the gas gets to the black hole, the faster it generally has to orbit, and the disk becomes an environment of extreme turbulence, magnetic activity, compression, and internal friction-like stresses. These processes convert part of the gas's orbital and gravitational energy into heat before the material ever disappears. In stellar systems containing a relatively small black hole, the inner regions of the disk can reach temperatures of millions of degrees, far hotter than the visible surface of the Sun and hotter than the surfaces of most normal stars. At such temperatures, the disk does not simply glow red or white like heated metal. Much of its energy emerges as X-rays, which is one reason astronomers often discover feeding black holes using space telescopes designed to detect high-energy radiation rather than ordinary visible light. This leads to an important correction to the familiar image of a black hole as something that merely consumes whatever approaches it. Before matter is lost, it can release an enormous fraction of its available energy. In fact, accretion onto a black hole can convert matter's gravitational energy into radiation with an efficiency far greater than ordinary nuclear burning in a star. The exact temperature and appearance depend on the black hole's mass, how quickly material is arriving, the structure of the magnetic fields, and where in the disk you're looking. Curiously, disks around the most enormous black holes are not necessarily the hottest ones. Their inner disks can peak at lower temperatures than those around smaller stellar black holes, even though the total system may produce vastly more energy because it is processing far more material. Above and around the disk, there may also be an extremely hot, thin region of energized particles that can boost lower energy photons into the X-ray range, creating a high-energy glow that reveals conditions very close to the black hole without requiring us to see the black hole itself. Astronomers study changes in this radiation to learn how the flow behaves, how rapidly material is moving inward, and how energy is transported through an environment where gravity dominates everything nearby. So the brightest part of a black hole system is often not the black hole at all, but the last visible chapter of matter before it crosses beyond our reach. There is something almost paradoxical about that. The object, famous for trapping light, can create, indirectly, a surrounding region that shines more fiercely than the stars around it. Darkness does not announce itself by glowing, but matter struggling at its edge does. And by studying that final burst of heat, you can learn about a place that can never send you a message from the other side. One stellar explosion can temporarily outshine an entire galaxy. For a few extraordinary days, one dying star can become brighter than billions of living stars around it. This is the astonishing scale of a supernova. A single stellar explosion can increase in brightness so dramatically that, from another galaxy, it may rival or even exceed the combined visible light of the galaxy that contains it. The effect is not because the star suddenly becomes physically larger than its galaxy, but because an enormous amount of stored energy is released into a relatively small region and then converted into radiation. In one major class of supernova, a massive star reaches the end of its ability to generate energy in its core and undergoes catastrophic collapse, launching material outward at thousands of kilometers per second. In another important class, a white dwarf in a binary system is pushed into a thermonuclear runaway that destroys the star. The details differ, but both can produce a rapidly expanding cloud of extremely hot material, whose brightness rises enormously before gradually fading. What you see from a distant telescope is therefore not a single flash in the ordinary sense. A supernova can brighten over days or weeks and remain visible for months, changing color and producing a recognizable pattern as its expanding debris cools. One reason the glow can continue long after the initial explosion is radioactive decay. Certain unstable elements created during the event transform into other elements, releasing energy that keeps heating the expanding debris from within. In many supernovae, radioactive nickel becomes cobalt and then iron, helping power the fading light that astronomers continue to observe after the initial violence has passed. By measuring how the brightness changes with time and separating the light into its component colors, researchers can identify chemical elements in the debris, estimate how quickly material is moving, and learn what kind of star exploded. Some explosions are especially extreme. Rare superluminous supernovae can remain dramatically brighter than ordinary supernovae and may require additional sources of energy beyond the standard radioactive picture, such as interaction with dense material surrounding the star or energy injected by a rapidly rotating compact remnant. Yet even an ordinary supernova can perform an impressive visual trick. A galaxy that looked like a smooth collection of billions of distant stars suddenly develops one point of light bright enough to compete with the whole background. This does not mean the supernova releases more total energy than every star in the galaxy over their entire lives. The comparison concerns brightness during a brief interval. A galaxy shines continuously for billions of years, while a supernova spends its energy in a short, spectacular episode. That difference between power and duration is what makes the event seem almost unreasonable. It is like comparing a city that uses electricity steadily through the night with a lightning strike that releases its energy in an instant. The shorter event can briefly become overwhelmingly brighter even though it cannot sustain that output. And supernovae matter for reasons far beyond spectacle. Their expanding debris helps return elements to interstellar space, and the shock waves can disturb surrounding clouds from which later generations of stars may form. Astronomers also use certain supernovae to measure enormous cosmic distances because their brightness can be calibrated well enough to act as distance indicators. So when a single point suddenly challenges the light of an entire galaxy, you are not merely witnessing the dramatic death of one star. You are watching stellar evolution, nuclear physics, galactic chemistry, and even cosmology become visible in the same event. A star that spent millions or billions of years quietly obeying gravity can end with a brief period in which it becomes one of the most noticeable objects in its galaxy, and then it fades again, leaving behind expanding debris and information that can travel across space long after the star itself is gone. Gamma-ray bursts can release enormous energy in only seconds. Sometimes the universe does not brighten gradually at all. Without warning, a spacecraft detects a burst of gamma rays from deep space, and within seconds, one of the most energetic events known may already be nearly over. Gamma-ray bursts are extraordinarily intense flashes of the highest energy form of electromagnetic radiation, and their defining mystery was once not only how powerful they were, but where they came from. Because Earth's atmosphere absorbs most gamma rays before they reach the ground, these events were first discovered using instruments in space, and for years they appeared as brief flashes with no obvious visible source. Modern observations have revealed that gamma-ray bursts are not all produced in the same way. Astronomers broadly divide them into long and short bursts, based largely on how long the main gamma-ray emission lasts. Many long bursts are associated with the deaths of unusually massive stars, while many short bursts are connected to mergers involving compact stellar remnants. What both categories can produce is an extraordinarily fast release of energy concentrated into narrow jets moving outward at speeds extremely close to the speed of light. This focusing is crucial to understanding why gamma-ray bursts can look so impossibly powerful. If you assumed the radiation was being emitted equally in every direction, the calculated energy could appear enormous even by cosmic standards. In reality, much of the emission is often directed into relatively narrow beams. If Earth happens to lie inside one of those beams, we see an intense burst. If the jet points elsewhere, the event may be almost invisible to gamma-ray detectors on our planet. This means there are probably many such events we never recognize as gamma-ray bursts simply because their beams miss us. Inside the jet, matter and energy move so rapidly that collisions, shocks, and magnetic processes can accelerate particles and generate gamma rays. The exact mechanism responsible for converting the jet's energy into the radiation we observe remains an active area of research, which is why scientists study the detailed flickering of each burst rather than treating it as one simple flash. Some gamma-ray bursts change dramatically in milliseconds, telling you that whatever is producing the emission must involve extraordinarily compact regions and extremely rapid processes. Yet the disappearance of the gamma rays is not necessarily the end of the event. As the outward-moving material crashes into gas surrounding the source, it can produce an afterglow visible in X-rays, ultraviolet light, visible light, infrared, and radio waves. These afterglows can last far longer than the original burst and allow astronomers to determine the host galaxy, measure distance, study the surrounding environment, and sometimes identify what kind of catastrophe produced the jet. One of the most striking consequences is that a burst lasting only seconds can be detected from billions of light years away. The photons reaching a satellite today may have begun their journey when the universe was dramatically younger, meaning the detector is receiving not simply an energetic flash, but a time capsule from an ancient galaxy. Gamma-ray bursts can therefore help scientists study star formation and extreme physics at distances where many ordinary stars are impossible to examine individually. They also demonstrate how misleading duration can be when you judge importance. Human intuition often associates powerful events with long events. Mountains rise slowly, stars live for millions of years, galaxies evolve over billions. Gamma-ray bursts reverse that expectation. A process lasting less time than a conversation can release an extraordinary amount of energy and send radiation across a significant fraction of the observable universe. The event is brief only where it begins. Its consequences spread outward for billions of years, eventually reaching detectors built by beings who did not exist when the burst occurred. And that leaves you with a strange way to think about cosmic time. Some of the shortest events in the universe can leave behind some of the longest journeys. White dwarfs can hold the mass of the sun inside a body the size of Earth. One day, our own sun will leave behind something so compact that almost all of its remaining mass could fit inside a sphere roughly the size of Earth. And yet that object will no longer be a normal star at all. This is a white dwarf, the exposed remnant left when a star similar to the sun reaches the end of its nuclear burning life, swells into a giant, and eventually sheds its outer layers into space. What remains is the former core, usually made mostly of carbon and oxygen, containing a large fraction of the original star's mass in a volume millions of times smaller than the sun. The strange part is what holds it up. A normal star resists gravity because energy produced by nuclear fusion creates enough outward pressure to balance the inward pull. But a white dwarf has largely finished that kind of energy production. Its survival depends instead on a quantum rule governing electrons. Electrons cannot all be forced into exactly the same available states. So when matter is squeezed to extraordinary density, this restriction creates a powerful resistance to further compression. This is known as electron degeneracy pressure, but you do not need the terminology to understand the idea. Gravity keeps trying to crowd the material more tightly, while the quantum behavior of electrons refuses to let matter be compressed without limit. The result is an object with a surprising property. For ordinary objects, adding more mass usually makes them larger. For white dwarfs, adding mass can actually make them smaller because stronger gravity compresses the interior more severely. There is, however, a boundary to how far this can go. A white dwarf cannot remain stable above roughly 1.5 times the mass of the Sun, with the exact value depending on its composition and rotation. Approach that limit, and the electrons can no longer provide enough support in the same way. This limit became one of the great clues, showing that stellar remnants are governed not only by gravity, but by quantum physics on an astronomical scale. A typical white dwarf may have a surface gravity tens or hundreds of thousands of times stronger than Earth's, so a person could never stand on one, and any familiar material placed there would behave in conditions far outside ordinary experience. Yet white dwarfs are not simply dark cinders. When they first form, they are intensely hot, glowing because of heat stored from their earlier life, and then they cool gradually over billions of years. They are not being powered like ordinary stars. They are slowly releasing energy they already possess. Given enough time, a white dwarf would eventually cool toward a dark, cold remnant, sometimes called a black dwarf. But the universe is not yet old enough for any true black dwarfs to have formed. That fact gives you an unusual way to look at a white dwarf. It is both an ending and a clock. Its temperature contains information about how long it has been cooling, allowing astronomers to estimate the ages of old groups of stars. And perhaps the most revealing part is that the object looks deceptively simple from a distance. A faint point of light can hide nearly a sun's worth of matter compressed into something no larger than a planet, supported not by fire, but by a rule written into the behavior of particles. A white dwarf shows you that when a star's familiar source of power disappears, nature does not necessarily allow gravity to finish the job. Sometimes an invisible quantum restriction becomes strong enough to hold up an entire star. Two dead stars can merge and create gold and other heavy elements. The gold in a ring can carry the chemical fingerprint of an event so violent that it may have happened billions of years before the solar system existed. Some of the heaviest elements in nature cannot be produced efficiently by the slow nuclear processes that operate through most of a star's lifetime, because building nuclei as heavy as gold, platinum, and many other rare elements requires an environment flooded with neutrons. One of the most powerful known places where such conditions arise is the merger of two neutron stars, the compact remains of stars that died long ago. When these two remnants finally come together, some of their neutron-rich material can be torn away and thrown outward before it is swallowed or incorporated into the object left behind. What happens inside that expanding debris is one of the most remarkable examples of cosmic chemistry. Atomic nuclei are exposed to such an intense supply of neutrons that they can capture them faster than unstable nuclei have time to decay. The nuclei rapidly become extremely neutron-rich, then transform through a chain of radioactive decays into a wide range of heavy elements. This process is called rapid neutron capture, and it is one of the leading explanations for the cosmic origin of elements such as gold, platinum, europium, and several others heavier than iron. The important point is that the gold is not sitting inside the original dead stars, waiting to be released. Much of it is assembled during and immediately after the merger, as the ejected nuclear material changes into new elements. As those freshly created unstable nuclei decay, they release heat into the expanding debris, producing a distinctive glow known as a kilonova. Unlike a normal stellar explosion, its light changes rapidly over days and shifts in color as the debris expands and different elements influence how radiation escapes. In 2017, astronomers were able to observe such a neutron-star merger across many kinds of light, and the changing glow provided some of the clearest evidence that these events really do manufacture heavy elements in significant quantities. Researchers still debate exactly how much of each element comes from neutron-star mergers compared with other rare astrophysical environments. So it would be misleading to say that every atom of gold in the universe must come from this single source. But there is now strong evidence that these mergers are major factories for many of the heaviest elements. The journey does not end when the elements are created. The debris spreads into interstellar space, becomes mixed with gas and dust, and can later be incorporated into new generations of stars, planets, asteroids, and eventually living worlds. The gold on Earth therefore had to survive an extraordinary sequence: nuclear creation in an ancient catastrophe, dispersal through a galaxy, incorporation into the cloud that formed the solar system, concentration inside a young planet, and geological processes that eventually place some of it close enough to the surface for humans to find. Seen this way, a piece of gold is not merely valuable because it is rare or beautiful. It is evidence that matter can remember environments that no longer exist. Something you can hold between two fingers may contain atoms assembled when two dead stars met in a place you will never see, under conditions that lasted only briefly, and yet those atoms remained stable enough to travel through cosmic history until they became part of your world. A star can orbit the black hole at the center of our galaxy at extreme speed. Deep in the center of the Milky Way, there are stars moving so fast that astronomers can watch their positions noticeably change over only a few years, as if the crowded heart of the galaxy were running on a completely different clock from the quiet neighborhood around our sun. One particularly well-studied star follows a highly stretched orbit around the enormous black hole at the center of our galaxy, completing one full journey in only about 16 years. That may sound slow until you remember the scale involved. The star is traveling across a region large enough to swallow our solar system many times over, and when it reaches the closest part of its orbit, it accelerates to roughly 25 million kilometers per hour, several percent of the speed of light. The star does not move at that speed during its entire orbit. Farther away, it travels more slowly. Then gravity accelerates it dramatically as it falls inward, just as a comet speeds up when approaching the sun, only on a vastly more extreme scale. What makes this orbit scientifically extraordinary is that astronomers have followed it for decades with powerful infrared telescopes, capable of seeing through the dust that hides the galactic center from ordinary visible light observations. By recording the star's position again and again, they can reconstruct its complete path and calculate the mass of the invisible object controlling it. The answer is astonishingly concentrated. Roughly 4 million times the mass of the Sun must be packed into a region small enough that the most convincing explanation is a supermassive black hole. In this sense, the star acts almost like a test particle placed there by nature. You cannot see the central black hole directly in the same way you see a star, but you can watch what its gravity makes nearby stars do. The orbit has also revealed something subtler. In a perfectly simple Newtonian system, the star would return along essentially the same ellipse each time, but careful observations show that the closest point of the orbit gradually shifts. The orbit slowly rotates within its own plane, an effect predicted by Einstein's description of gravity. This is important because it allows astronomers to test gravitational physics in a region far more intense than anything available in the solar system. And the central star field contains more than one fast-moving object. Researchers track many stars with different orbits, using them to estimate how mass is distributed near the center and to search for anything that might disturb their paths. Their motion has transformed what would otherwise be an inaccessible dark region into something measurable. There is also a striking difference between your position in the galaxy and theirs. The Sun takes roughly hundreds of millions of years to complete one orbit around the Milky Way, so no human civilization could ever watch a full galactic year unfold. Yet near the center, astronomers have already observed a single star complete an entire orbit within the span of a scientific career. That contrast gives you an unusual sense of how gravity organizes motion. The galaxy is not rotating like a rigid wheel where every star moves together at one pace. Different environments create radically different journeys. Near the center, a star can race around an unseen mass at millions of miles per hour and return to the same region before a child born at the beginning of the orbit has reached adulthood. And by watching that star move, you learn something almost philosophical without needing to leave the science behind. Sometimes the clearest way to discover what cannot be seen is not to search for the hidden object itself, but to study the paths of everything that cannot escape its influence. Gravity can bend light enough to create multiple images of the same galaxy. The next time you see two distant galaxies in a telescope image, there is a strange possibility worth remembering. Sometimes they are not two galaxies at all, but two versions of the same one created because gravity has forced its light to take different routes toward you. Light normally feels like the most reliable messenger in the universe because once it leaves an object, it travels along the straightest path available. But the meaning of straight changes when space is curved by a large concentration of mass. If a distant galaxy lies far behind another massive object from our point of view, the space around the foreground object can bend the paths of light coming from the background galaxy. Some light may pass around one side, some around another, and several of those paths can eventually arrive at Earth. A telescope can then record the same distance source in more than one position on the sky. Nothing has duplicated the galaxy. You are receiving different bundles of photons that left the same object but traveled through different regions of curved space before reaching you. The arrangement does not always produce neat, identical copies. Depending on how the source, the foreground mass, and Earth are aligned, the images can appear stretched, magnified, distorted, or broken into long arcs. Some may be brighter than others because the bending magnifies one light path more strongly, and some can even appear flipped in orientation. This phenomenon is called gravitational lensing because gravity behaves in certain ways like an enormous natural lens, although unlike a glass lens, it has no physical surface. The lens is the curved geometry created by mass. One of the most useful consequences is that distant galaxies too faint to study clearly on their own can sometimes become magnified enough for astronomers to examine them in greater detail. Nature is effectively providing part of the telescope, but multiple images reveal something even more subtle. The different light paths do not usually have exactly the same length or pass through identical gravitational conditions, so the photons in each image can arrive at different times. If the distance source changes brightness, astronomers may see that change first in one image and days, months, or even years later in another. You can therefore look at several images of the same object in one photograph, while actually seeing that object at slightly different moments in its own history. This has allowed astronomers to measure what are called time delays and use them to learn about the lensing system and cosmic distances. Lensing is also a powerful reminder that astronomical images are not simple photographs of where objects really are. Every image of the deep universe has been shaped by the journey its light survived before reaching us. Usually that journey changes direction only slightly, but in the presence of enough mass, the distortion becomes visible, and one galaxy can appear scattered across the sky in several places at once. The effect does not violate the rule that light follows consistent physical laws. It demonstrates those laws more completely. Light is not being confused about which direction to travel. It is following the geometry available to it along several possible paths, and that changes the way you might think about seeing itself. When you look into deep space, position is not always a simple statement of location. A bright patch on the sky may be an image displaced from its source. Another nearby patch may be the same object viewed along a different route, and the universe between you and that galaxy may be acting as part of the optical system. What appears to be duplication is really geometry made visible, showing you that gravity can shape not only how matter moves, but also the very paths by which distant reality reaches your eyes. A galaxy behind another galaxy can appear as a perfect ring of light. Sometimes, a galaxy does not look like a galaxy at all. Under an almost impossibly precise alignment, it can appear as a glowing circle wrapped around another galaxy in the foreground. This strange shape is called an Einstein ring, and it forms when three things happen to line up unusually well: a very distant galaxy, a massive object between it and us, and Earth itself. The foreground galaxy bends the paths of light arriving from the more distant one, but when the alignment is nearly symmetrical, the bending happens around the foreground object in every direction, rather than producing just a few separate arcs. To your telescope, the background galaxy can then be stretched into a complete or nearly complete ring of light. Nothing in the distant galaxy has physically become circular, and no luminous shell has formed around the nearer one. The ring is an optical consequence of gravity acting on the light during its journey. Even more remarkably, the diameter of that ring contains information. By measuring its size and shape, astronomers can estimate how much mass is concentrated in the foreground system, including mass that does not emit any light of its own. This makes Einstein rings useful for mapping the distribution of matter inside galaxies and galaxy clusters, not merely for producing beautiful telescope images. The ring can also magnify the background galaxy, allowing astronomers to examine objects that would otherwise be too faint or too distant to study in detail. Features such as star-forming regions, gas clouds, or young stellar populations can become stretched and enlarged across the arc, effectively giving our telescopes additional resolving power supplied by the universe itself. But a perfect ring is rare because the alignment must be extraordinarily close. Shift the background source slightly to one side, and the ring breaks into arcs or multiple distorted images. Shift it farther still, and the effect becomes less obvious. So every nearly complete Einstein ring is a clue that you are looking almost directly down a very specific line through cosmic space, with objects separated by billions of light years accidentally arranged with astonishing precision from your point of view. There is another subtle lesson hidden in the shape. You are not seeing the distant galaxy in the position where its light appears to be. The foreground gravity has redirected the light before it reached you, so the ring is a map of possible light paths rather than a direct outline of the source itself. Astronomers have to model the foreground mass and mathematically reconstruct the original background galaxy from its distorted image, almost like reversing the effects of a warped piece of glass. In doing so, they can sometimes discover galaxies from periods when the universe was much younger and explore details that would otherwise remain unresolved. What first looks like a perfect cosmic ornament is therefore doing several jobs at once, revealing hidden mass, magnifying the distant universe, testing our understanding of gravity, and showing how dramatically appearance can depend on everything that lies between an object and the observer. The ring is real as an image, but not as a structure surrounding the foreground galaxy, and that distinction quietly changes how you think about astronomical seeing. The sky is not simply a flat collection of objects sending light directly toward you. It is a layered landscape in which one galaxy can reshape the appearance of another without ever touching it, and a circle of light can be the visible signature of an alignment stretching across billions of years and billions of light years. We can detect invisible objects by watching them bend. Background starlight. An object can be completely dark, too faint to photograph, and still reveal its existence by briefly making another star appear brighter. This is the idea behind gravitational microlensing, one of astronomy's cleverest ways of finding things that produce little or no detectable light of their own. Imagine a distant background star shining steadily toward Earth. Now suppose another object passes almost exactly between that star and us. The foreground object might be a faint star, a planet, a compact stellar remnant, or something else difficult to see directly. Its gravity bends the background star's light very slightly, redirecting additional light toward us. Because the separation is usually far too small for telescopes to resolve multiple images, we do not see a ring or a collection of distorted copies. Instead, the distant star simply appears to brighten for a while and then fade back to normal as the alignment changes. The characteristic rise and fall of that brightness is what astronomers search for. The foreground object never needs to shine. It only needs mass. This makes microlensing especially valuable for detecting populations that ordinary surveys can easily miss, including planets orbiting far from their stars, free-floating planets that may have no host star at all, and dark stellar remnants such as isolated black holes or neutron stars. The duration of a microlensing event can provide important clues. Some last only hours or days, while others can persist for months or even longer, depending on the mass of the lensing object and how quickly the alignment changes. If the foreground object is a star with a planet, the planet's gravity can briefly distort the otherwise smooth brightening pattern, producing an additional feature that may last for only a short time. From that tiny deviation, astronomers can infer the presence of a world that might be thousands of light years away and far too dim to photograph directly. Microlensing has a peculiar disadvantage, however, that also makes every detection feel almost accidental. Most events do not repeat. Once the foreground object has moved away from the narrow alignment, the same geometry may never happen again during a human lifetime. Astronomers therefore have to monitor enormous numbers of stars continuously, especially toward crowded regions of the Milky Way, waiting for one of them to brighten in exactly the right way. Careful analysis is also required, because stars can brighten for many reasons unrelated to lensing. So researchers compare the shape of the light curve, its behavior in different colors, and sometimes tiny shifts in the apparent position of the background star to determine what is happening. For particularly long events, that positional shift can help estimate the mass of the invisible lens and distinguish a massive dark remnant from an ordinary faint star. This turns an apparent absence into something measurable. You may have no photograph of the foreground object, no reflected light from its surface, and no glowing gas surrounding it. Yet its gravity leaves a temporary fingerprint on a completely unrelated star behind it. That is what makes microlensing such a powerful idea. Astronomy usually feels like the science of collecting whatever light reaches us. But here, the missing object is discovered through what it does to someone else's light. You do not see the object itself. You see a background star brighten because an unseen mass briefly rearranged the path between that star and your telescope, and that suggests a broader way of thinking about the universe. Invisibility is not the same as absence. Something can remain completely dark and still alter the scene around it, strongly enough for careful observers to know that it was there. Some planets orbit so close to their stars that their atmospheres are boiling away. There are planets so close to their stars that the sky above them is not simply hot, it is slowly escaping into space. These worlds complete an orbit in only a few days, sometimes even less, and they receive an intensity of stellar radiation that would be unimaginable anywhere near Earth. The most vulnerable part of an atmosphere is its thin upper edge, where gas particles are already only loosely held by the planet's gravity. Flood that region with powerful ultraviolet and X-ray radiation from a nearby star, and the gas can become heated to thousands of degrees. At those temperatures, the atmosphere expands far beyond the visible outline of the planet, and some of it begins flowing outward fast enough that gravity can no longer pull it back. This is not quite the same as water boiling in a pot. Astronomers call the process atmospheric escape, and in its most extreme form, the heated gas behaves almost like a planetary wind, carrying material continuously away from the world. Hydrogen is especially easy to lose because it is light, and astronomers have actually detected enormous clouds of hydrogen extending far beyond some close orbiting planets, sometimes forming tails that resemble the shape of a comet. More recently, helium has also become a powerful way to trace escaping atmospheres, because it can absorb a specific wavelength of infrared light as a planet passes in front of its star. By watching that absorption change during a transit, researchers can detect gas occupying a region much larger than the planet itself. The consequences can unfold over hundreds of millions or billions of years. A planet that began with a thick envelope of hydrogen and helium may gradually be stripped down, potentially exposing a smaller, denser core underneath. This process may help explain why astronomers find relatively few medium-sized planets extremely close to their stars. Some worlds may once have been larger gaseous planets, but lost much of their outer atmosphere under relentless radiation. The star itself also changes with age, and young stars can be particularly violent sources of high-energy radiation, meaning a planet's earliest history may determine whether it keeps its atmosphere for the rest of its existence. Yet atmospheric loss is not automatic destruction. A massive planet with strong gravity can hold onto gas far more effectively than a smaller one, and the rate of escape depends on the planet's temperature, composition, magnetic environment, distance from its star, and the star's activity. Some planets may lose only a fraction of their atmosphere, while others may be transformed completely. This makes close orbiting planets valuable, because you are not merely observing what a planet is today, you may be catching it during a long process of becoming something else. A swollen atmosphere drifting into space is a record of competition between radiation and gravity, between what the planet inherited when it formed and what its star has been taking away ever since. And that raises a quiet question about the planets we classify so confidently as rocky, gaseous, or somewhere in between. How many of them were born looking entirely different? A planet may seem like a finished object when you see it in a catalogue, but near a powerful star its atmosphere can still be changing, particle by particle. With the world you observe today only one temporary stage in a history written partly by what it has already lost. There are planets where it may rain molten rock. On some distant worlds, the weather forecast may involve clouds made from vaporized stone and rain that would solidify into rock instead of water. This sounds like fantasy until you consider what happens to a rocky planet orbiting extremely close to its star. On certain ultra-hot planets, temperatures on the permanent Dayside may rise high enough to melt large regions of the surface, creating oceans of magma rather than liquid water. Many of these worlds are probably tidally locked, meaning one hemisphere continually faces the star while the opposite side remains turned toward darkness. That creates an extraordinary contrast. The Dayside can become hot enough not only to melt rock, but to vaporize some of its minerals into a thin atmosphere, while the night side may be vastly cooler. Under those conditions, the planet can develop a kind of rock cycle, unlike anything operating naturally on modern Earth. Minerals containing elements such as sodium, silicon, oxygen, iron, or other components of ordinary stone can enter the atmosphere above the molten surface. Powerful winds may then carry some of this vapor away from the hottest region toward cooler parts of the planet. As the gas cools, mineral compounds can condense into droplets or particles and fall toward the surface. In that sense, researchers have proposed that some lava worlds could experience something reasonably described as rock rain. It is important, though, not to turn a scientific model into an eyewitness report. No spacecraft has stood beneath one of these skies and photographed droplets of molten stone falling from the clouds. The idea comes from combining measured planetary properties, such as size, orbital period, stellar heating, and temperature differences, with models of how silicate-rich material should behave under those conditions. One particularly studied lava planet appears to have such an extreme difference between its blazing Dayside and much colder night side that researchers have modeled a cycle in which vaporized rock is transported through the atmosphere, condenses on the cooler hemisphere, and may eventually return toward the hot side through flows of molten material. The result would be a planetary circulation system in which the substance moving through the atmosphere is not primarily water, but the very material of the crust itself. Even the word ocean becomes strange here. A magma ocean is not necessarily a deep global sea like Earth's oceans. It may be a vast region of molten surface rock maintained by constant stellar heating. The atmosphere above it can also be surprisingly thin, because heavy mineral vapor behaves very differently from the thick hydrogen atmospheres of giant planets. That means the weather could be violent and alien without requiring an enormous blanket of gas. Studying these worlds matters because their exposed surfaces allow astronomers to investigate what rocky planets are made of under conditions where geology and atmosphere are directly connected. On Earth, rock usually seems permanent on human timescales. It forms mountains, coastlines, buildings, and the ground beneath your feet. On a lava planet, that same category of material may evaporate, move through the sky, condense, fall, melt again, and circulate across the world. The chemistry has not become magical. Only the temperature has changed enough to make familiar matter behave in unfamiliar ways. And perhaps that is what makes these planets so revealing. They remind you that concepts like rain, ocean, cloud, and weather are not tied to water. They are patterns of matter moving between different states. Change the environment dramatically enough, and even stone can become part of the sky. Some worlds may have clouds made of vaporized metals. If you could somehow look up from the atmosphere of certain scorching exoplanets, the clouds above you might contain substances that on Earth belong inside rocks, machines and metal objects rather than in the sky. This becomes possible on worlds heated to temperatures of thousands of degrees, especially giant planets orbiting extremely close to their stars, where familiar assumptions about what can become a gas begin to break down. On Earth, metals such as iron remain solid or molten under most natural surface conditions, but raise the temperature enough, and even these materials can enter the atmosphere as vapor. The remarkable part is that an ultra-hot planet is rarely heated evenly. Its star-facing hemisphere can become enormously hotter than the side facing away, while powerful atmospheric winds continuously transport gas from one region to another. Material that exists as vapor in the hottest part of the atmosphere may therefore be carried toward cooler regions, where the temperature falls below the point at which it can remain gaseous. There, atoms and molecules can begin gathering into tiny condensate particles, creating clouds made from materials radically different from Earth's water droplets or ice crystals. Depending on the temperature and chemistry of a particular world, scientists expect cloud particles containing iron, silicates, aluminum compounds, or other heat-resistant substances that normally make up minerals deep inside planets. Astronomers cannot scoop these clouds into a container, so they study them through light. When a planet passes in front of its star, some starlight filters through the planet's atmosphere before reaching our telescopes. Different atoms, molecules, and cloud particles remove or scatter particular parts of that light, leaving patterns that can reveal what is present. By comparing the atmosphere near the evening side of a planet with the atmosphere near the morning side, researchers can even find evidence that materials are distributed unevenly, as though the planet has different chemical weather systems depending on which direction the winds have carried them. This is especially important because clouds can hide deeper layers of an atmosphere, making a planet appear chemically simpler than it really is. A cloud deck composed of exotic minerals can block wavelengths that would otherwise reveal gases beneath it. So understanding the clouds becomes necessary before scientists can understand the planet itself. These atmospheres also show how misleading everyday categories can be. You naturally separate air from rock because Earth's temperature allows those materials to occupy very different environments, but that division is not a universal rule. Change the temperature enough, and the boundary between geology and weather begins to disappear. Material that would form a mountain on one world can become atmospheric vapor on another, travel with winds, condense into microscopic particles, and eventually return to deeper layers. The physics is not exotic because the substances are imaginary. It is fascinating precisely because they are ordinary elements behaving under extraordinary conditions. A sky filled with metallic or mineral clouds is therefore more than a strange image. It is evidence that weather is really chemistry responding to temperature, pressure, and motion, and those conditions can vary far beyond anything your own planet prepared you to expect. The deeper lesson is quietly simple. When you look at a cloud on Earth, you are not seeing what clouds must be made of. You are only seeing what clouds happen to be made of here. A planet can orbit two stars at the same time. A world can have two suns in its sky and still follow a stable orbit for millions or even billions of years, despite what your intuition might tell you about two stars constantly pulling it in different directions. These are known as circumbinary planets, worlds that travel around a pair of stars rather than belonging to only one of them, and their existence was once much harder to confirm than ordinary planets, because the motion of the system is considerably more complicated. The two stars orbit a shared center of mass, continually changing their positions relative to the planet, while the planet follows a much wider path around both of them. At first, this might sound gravitationally chaotic, as though the world should eventually be thrown away or dragged into one of the stars. And indeed, there are regions close to a binary pair where planetary orbits can become unstable. But farther out, beyond a critical distance, the combined gravitational influence of the two stars can behave regularly enough for a planet to survive. Instead of responding independently to every motion of each star, the distant planet largely orbits their combined mass, while experiencing smaller gravitational variations as the stars circle one another inside its path. Astronomers have discovered several such worlds, confirming that planet formation can succeed even in environments that once seemed too dynamically complicated. Detecting them is particularly interesting because a normal planetary transit is already a matter of precise alignment. The planet must cross in front of its star from our perspective and dim the starlight slightly. With two stars moving around each other, the timing and duration of those crossings can change dramatically. A planet may pass in front of one star, later cross the other, then go through periods when the geometry prevents a visible transit altogether. Instead of perfectly repeating dips in brightness, astronomers look for a pattern whose irregularity is itself predictable once the three-body motion is understood. That changing pattern helped establish some of the first convincing examples of planets orbiting binary stars. If you could stand on one of these worlds, the sky would not necessarily resemble a simple science fiction scene in which two identical suns remain side by side. The stars might differ in size, color, and brightness, and their separation in the sky would continually change as they orbit each other. Sometimes they could appear far apart. At other times, they might approach one another visually or even eclipse each other, causing the total amount of daylight reaching the planet to vary. The planet's seasons could therefore depend not only on its own orbit and axial tilt, but also on the changing configuration of the stellar pair. Yet these systems are scientifically important for another reason. They challenge simple ideas about where planets can form. A young binary system contains a disk of gas and dust disturbed by the gravity of two moving stars. Collisions among growing planetary material can be faster and more disruptive than in a system like ours, and some regions may be hostile to planet formation altogether. The fact that circumbinary planets nevertheless exist tells astronomers that planetary systems are remarkably adaptable. Worlds can emerge from disks that are warped, stirred, and gravitationally complicated, then settle into stable paths that endure. So, a planet orbiting two stars is not merely an exotic variation of Earth with a prettier sunset. It is a demonstration that orbital order can emerge from a system that initially looks chaotic. Two stars can continually move, tug, eclipse, and exchange positions in the sky, while a planet traces a much larger path around them, reminding you that stability in the universe does not always mean simplicity. Sometimes it means many motions fitting together so precisely that what appears complicated from the outside can continue quietly for ages. Some planets wander through space without any star. Not every planet has a sunrise, because some worlds travel through the galaxy without belonging to any star at all. These are often called rogue planets, or free-floating planets, and their existence changes the familiar picture of a planetary system built around a central sun. A rogue planet may once have formed inside an ordinary young system, surrounded by other planets competing for space, while their orbits were still changing. In those early years, planetary systems can be surprisingly violent. Large worlds can repeatedly tug on one another, and a close gravitational encounter can transfer enough energy to send one planet onto a much wider orbit, while pushing another inward. If the encounter is strong enough, the unlucky world can be accelerated beyond the gravitational hold of its star and never return. Passing stars can also disturb young systems, especially inside dense stellar nurseries where stars form relatively close together, and those encounters can help remove planets from the systems that created them. There is even another possibility. Some planet mass objects may form directly from collapsing clouds of gas rather than being expelled from a planetary system at all, which makes the boundary between a very small failed star and a very large free-floating planet surprisingly difficult to define. Once separated from a star, such a world enters a radically different existence. There are no regular days or years defined by an orbit around a sun. The sky would be almost completely dark, except for distant stars, and the planet would receive no strong external source of warmth. Its surface would generally cool with time, but that does not necessarily mean the entire world becomes completely frozen and inactive. Large planets retain heat left over from their formation, and radioactive elements inside rocky worlds can continue producing internal energy for billions of years. A thick atmosphere, if the planet managed to keep one, could trap some of that heat, and theoretical models even allow the possibility that certain isolated worlds could maintain subsurface liquid environments under thick layers of ice. This does not mean rogue planets are secretly comfortable Earth-like worlds. Most would likely be extremely cold at their visible surfaces, and their actual conditions depend heavily on their mass, composition, age, and atmospheric history. Yet the possibility matters because it separates habitability from sunlight in a way that feels almost counterintuitive. Life on Earth depends overwhelmingly on the sun, so you naturally associate a star with every meaningful planetary environment. But internal heat can create another source of energy, especially beneath a surface shielded from the cold of space. A rogue planet could also carry moons with it, if those moons remained tightly enough bound during the event that expelled the entire system, creating a miniature wandering family traveling through the Milky Way together. None of this makes such planets easy places to find. Without a nearby star illuminating them, they are often extraordinarily faint, especially after they have cooled. Younger and larger rogue worlds can still glow in infrared light because they retain significant heat. But older and smaller objects may become nearly invisible against the darkness, and that may be the most compelling part of their existence. A planet does not stop being a planet simply because its star is gone. It can keep rotating, keep cooling, keep carrying an atmosphere or moons, and keep moving through the galaxy for billions of years with no sunrise waiting ahead. The word planet often makes you imagine a world defined by what it orbits. Yet rogue planets suggest a different definition. Sometimes a world can lose the center of its system and still continue as a world, carrying the physical memory of a star it may never encounter again. There may be billions of rogue planets drifting through the Milky Way. The empty space between the stars may be far more crowded with planets than it appears, and some estimates suggest the Milky Way could contain billions of worlds that no longer orbit any sun. The uncertainty in that number is enormous, because counting rogue planets is one of the hardest population surveys astronomers can attempt. Ordinary planets often reveal themselves because they repeatedly influence or pass in front of a host star, giving researchers many chances to confirm that the same object is there. A free-floating planet offers no such convenient anchor. It may be cold, dark, incredibly distant, and moving through a field crowded with unrelated stars, so researchers cannot simply photograph the galaxy and count isolated planetary dots. Instead, scientists build population estimates from rare detections and then ask how many unseen objects would need to exist for those detections to occur as often as they do. Different surveys have produced different answers, partly because they are sensitive to different ranges of planetary mass, and partly because a short, faint event can be difficult to distinguish from observational noise or other astrophysical effects. That is why headlines claiming a precise number of rogue planets should be treated cautiously. Astronomers are much more confident that free-floating planetary mass objects exist than they are about exactly how common each type is. The population itself may also span a huge range. Some wanderers could be massive gas giants comparable to Jupiter, which are relatively easier to notice while young because they remain warm. Others may be similar in mass to Neptune, Earth, or even smaller, becoming increasingly difficult to detect. If low-mass planets are frequently expelled during the chaotic formation of planetary systems, then the objects easiest to miss could actually be the most numerous. This possibility matters because the number of rogue worlds contains information about how planetary systems are built. If astronomers eventually find only a modest population, that would suggest most developing systems keep their planets relatively efficiently. If they find enormous numbers, then planetary formation may be far more wasteful and chaotic, producing many worlds that are later thrown away. The statistics could also tell researchers how often young planets migrate, how violently giant planets interact, and how strongly neighboring stars disturb developing systems. In that sense, invisible wanderers become a fossil record of planetary systems that may no longer resemble their original form. The Milky Way itself then begins to look different. You normally picture the galaxy as hundreds of billions of stars surrounded by darkness, with planets gathered close to those points of light. But if rogue planets number in the billions or more, a significant hidden population may exist throughout the spaces between stellar systems, following independent orbits around the center of the galaxy, just as stars do. They would not be evenly scattered, and they would not constantly pass near other solar systems. Interstellar distances remain enormous. Most could travel for immense spans of time without approaching another star closely enough to be captured. Occasionally, however, a wandering planet might pass through a new stellar neighborhood, and in rare circumstances, gravitational interactions could alter its path again. The larger scientific lesson is not that the galaxy is secretly packed like a crowded room, but that our visual picture of it is strongly biased toward anything that shines. Stars advertise themselves across vast distances. Rogue planets usually do not. So when astronomers estimate how many might be drifting unseen through the Milky Way, they are confronting a recurring problem in astronomy. The visible universe is not necessarily the complete universe. There may be an enormous population of worlds between the stars, and the reason they feel rare may simply be that darkness is exceptionally good at hiding what does not produce its own light. Some exoplanets are so hot that molecules are torn apart on their daysides. There are planets where crossing from night into daylight does not simply raise the temperature. It can change what the atmosphere is chemically allowed to be. On the hottest known giant exoplanets, the hemisphere facing the star can reach temperatures of several thousand degrees, comparable to the surfaces of some stars. And under that kind of heat, many familiar molecules cannot remain intact. Water vapor, for example, can be broken apart into smaller fragments, while molecular hydrogen, the ordinary form in which two hydrogen atoms travel together, can split into individual atoms. This is called thermal dissociation, and it happens because collisions become energetic enough to overcome the bonds holding molecules together. The atmosphere has not vanished, and the atoms themselves are not being destroyed. Rather, combinations that are stable in cooler conditions stop surviving on the intensely heated dayside. This creates an atmosphere that can be chemically different depending on where you look. Many of these worlds orbit so close to their stars that they are expected to keep nearly the same face pointed toward the light, leaving one hemisphere under continuous heating and the other in permanent darkness. Powerful winds still carry atmospheric material around the planet, however, and something remarkable can happen during that journey. Hydrogen atoms created by extreme dayside heat can flow toward cooler regions and recombine into hydrogen molecules. Forming those molecular bonds releases energy, while breaking them apart on the dayside absorbs energy. So the chemistry itself can help transport heat from one side of the planet to the other. In other words, part of the planet's temperature regulation may occur not merely because hot gas moves, but because energy is temporarily stored in broken chemical bonds and released again when those bonds reform. This is one reason scientists cannot understand these atmospheres simply by treating them as hotter versions of Jupiter. At extreme temperatures, the rules governing opacity, chemistry, clouds, and circulation all begin to change together. Some molecules that astronomers normally use to identify an atmosphere may become difficult to detect on the hottest hemisphere because they have been dissociated there, only to reappear where temperatures fall. Certain atoms and ions can become far more important, and free electrons interacting with hydrogen can create a broad atmospheric absorption that changes the planet's spectrum. Astronomers investigate these effects by measuring tiny changes in starlight as a planet passes in front of its star, and by watching how the planet's brightness changes throughout its orbit. From those measurements, they can build crude temperature maps, identify chemical species, and compare the day side with the night side even though the planet itself may be hundreds of light years away. The result is a kind of meteorology that has no close equivalent on Earth. Here, weather moves clouds and water through different phases. There, atmospheric circulation can repeatedly dismantle and rebuild molecules as gas crosses from one hemisphere to another. And this is what makes these planets more than examples of extreme heat. They show you that chemistry is not a permanent inventory written into a world at birth. The same collection of atoms can organize itself differently from one longitude to the next, simply because the energy available has changed. A molecule that exists on the night side may effectively disappear by noon and return again in darkness. So even the atmosphere of a planet can become a moving boundary between different versions of matter. A planet can be stretched into an egg shape by its star's gravity. A planet does not have to remain round if it lives too close to its star. Gravity can quietly reshape the entire world until one direction becomes longer than the others. Planets are normally close to spherical because their own gravity pulls material inward from every direction, smoothing out large irregularities over time. But a nearby star does not pull equally on every part of a planet. The hemisphere facing the star is slightly closer and therefore feels a stronger gravitational attraction, while the far side feels a somewhat weaker pull. Across an ordinary planetary distance, this difference may be small, but move the planet extremely close to its star, and the imbalance can become strong enough to deform the whole body. Instead of being a perfect sphere, the planet develops a tidal bulge aligned roughly toward and away from the star, producing an elongated shape that can resemble an egg or a rugby ball. This is not simply an atmosphere being blown outward. The planet's overall gravitational figure can be distorted, including its deeper layers. Giant planets are especially interesting because much of their volume is fluid rather than rigid rock, allowing their shapes to respond more readily to changing forces. The degree of deformation depends on several things at once: how massive the star is, how close the planet orbits, how strongly the planet's own gravity holds it together, and how its interior is structured. A world with a dense central concentration can respond differently from one whose mass is distributed more evenly, which means the shape itself can contain clues about what lies beneath the clouds. Astronomers cannot usually resolve such a distant planet well enough to photograph its outline directly, but they can search for its deformation in the way it blocks starlight. As an elongated planet moves across the face of its star, the projected area presented toward us changes subtly during the transit, altering the shape of the brightness dip by a tiny but measurable amount. With sufficiently precise observations, researchers can compare those changes with models and estimate how strongly the planet has been distorted. This opens an unusual route into planetary interiors. On Earth, geologists use seismic waves to learn what lies below the surface. On distant gas giants, astronomers may use the response of an entire planet to its star's gravity. There is also a limit to how extreme this deformation can become. Bring a planet progressively closer to its star, and eventually, the difference in gravitational pull across the world can become comparable to the planet's ability to hold itself together. Near that boundary, material may begin escaping preferentially toward the star, and beyond it the planet could be disrupted rather than merely stretched. Some close orbiting planets may therefore be living in a temporary stage between stable world and gradual destruction. Yet an egg-shaped planet should not be imagined as visibly wobbling like a soft balloon. The deformation is governed by gravity and internal pressure, and from the planet's own surface the curvature might still seem locally smooth. Only from a wider perspective would its departure from a sphere become obvious. That makes the idea strangely deceptive. A world can look normal beneath your feet, while its entire global shape has been altered by an object millions of kilometers away. A planet's outline, then, is not always something determined only by what the planet is made of. Sometimes its shape is also a record of where it lives, showing that even something as fundamental as the form of a world can be negotiated continuously between its own gravity and the gravity of the star it cannot escape. Some stars are so large that they would swallow the orbit of Jupiter. A star can become so enormous that if you placed it where the Sun is now, Earth, Mars, and even Jupiter could disappear beneath its outer layers. That sounds almost impossible when you first picture a star as a glowing ball with a clear edge. But the largest red supergiants and hypergiants are nothing like compact spheres with sharply defined surfaces. Some have measured or estimated radii more than 1,000 times larger than the Sun's, and at least a few extreme examples would extend beyond Jupiter's present orbit if moved into the center of our solar system. The surprising part is that becoming this large does not require a star to contain thousands of suns worth of mass. Stellar size and stellar mass are very different things. A massive star can expand tremendously late in its evolution because the structure of its interior changes as different nuclear fuels are used, causing its outer layers to respond by moving farther from the center. The material in those outer regions becomes incredibly spread out. If you could somehow travel through the upper atmosphere of such a star, you would not encounter a sudden solid boundary. You would pass through increasingly dense gas. And even astronomers have to define a star's radius, using the layer from which light can effectively escape, rather than a physical surface you could touch. This is why comparisons such as larger than Jupiter's orbit describe the scale of the visible stellar atmosphere, not a rigid shell extending through the solar system. The average density of a giant star's outer envelope can become astonishingly low, meaning that something can occupy an enormous volume without filling that volume with dense material. In that sense, the largest stars are less like gigantic versions of the Sun and more like immensely expanded atmospheres surrounding much denser interiors. Their surfaces are also anything but calm. Giant convection cells can move vast amounts of hot gas, while pulsations and changing opacity can make the outer layers swell and contract. Astronomers sometimes find that estimating the exact diameter of these stars is difficult because their atmospheres are extended, irregular, dusty, and constantly changing. Even the phrase "largest known star" can shift as measurement methods improve and as researchers decide exactly where the effective edge should be placed. What remains secure is the scale. Nature can inflate a star until the distance from its center to its visible atmosphere is comparable to the dimensions of a large part of our planetary system. And yet, strangely, a planet placed deep inside that imagined star would not be surrounded by something resembling the dense interior of the Sun at every point. Much of the vast outer volume would consist of very thin, hot gas, whose density rises only gradually as you travel inward. That distinction matters because the true wonder is not simply that a star can become bigger than Jupiter's orbit. It is how delicately gravity can hold such an extended structure together at all. You are looking at an object with no solid walls, no fixed coastline, and an atmosphere spread across distances that light itself needs significant time to cross. A star can therefore be enormous without being uniformly massive, and perhaps that is what makes these giants so difficult to imagine correctly. Your intuition tells you that something larger must also be more solid and more crowded with matter, while the universe shows you the opposite. A star can grow to a size that could engulf worlds largely by becoming more diffuse, turning the familiar idea of a stellar surface into a boundary that is less like a wall and more like a fading transition between star and space. The most massive stars can lose several suns worth of material before they die. Some of the most massive stars spend the final part of their lives slowly dismantling themselves, throwing away an amount of matter that could have built several entire suns before their lives are over. They do this because an extremely luminous star is not merely shining into space. Its radiation is constantly interacting with material in its atmosphere, and under the right conditions, that outward flow of light can help accelerate gas away from the star. The result is a stellar wind, but calling it a wind can make the process sound gentle. In the hottest and most luminous massive stars, streams of charged particles can leave the surface at millions of kilometers per hour, continuously carrying the star's own mass into surrounding space. The rate is not the same throughout the star's life. As the star evolves, changes in temperature, luminosity, chemistry, and surface structure can strengthen or weaken the outflow, and some stars enter brief phases in which mass loss becomes especially severe. One famous class of stripped massive stars can shed roughly a sun's worth of material on timescales of around 100,000 years. While individual objects show that the total loss can be much larger, one well-observed massive star currently surrounded by its own expelled material has already lost about 10 suns worth of mass. This escaping material does not vanish. It creates shells, arcs, bubbles, and complicated clouds around the star, sometimes extending across several light years. Later, faster winds can crash into slower material expelled earlier, compressing it into glowing structures and heating gas at the collision boundaries. In this way, the region around a massive star becomes a layered record of its recent history. Astronomers can examine the speed, composition, and shape of the surrounding gas and infer that the star has gone through different episodes of mass loss, almost as though the star has left earlier versions of itself scattered through space. The composition of the wind can change too. Once enough of the outer hydrogen-rich material is removed, deeper layers that were previously hidden can become exposed, allowing astronomers to see products created by nuclear reactions that once occurred far beneath the surface. This means stellar winds do more than reduce a star's weight. They can physically peel back its structure and alter what kind of star it appears to be. Exactly how quickly massive stars lose matter remains an important scientific question because the winds are not perfectly smooth. They contain clumps and irregular structures, and estimates based on a smooth flow can give misleading answers. The chemical composition of the star also matters, because heavier elements provide many of the interactions through which radiation can push material outward. So massive stars born in different galactic environments may lose mass at different rates. Binary companions complicate the story further, because a nearby star can remove material gravitationally, meaning not every stripped massive star reached that condition through winds alone. This uncertainty has enormous consequences. The amount of mass a star retains changes its later structure, how much hydrogen remains around it, and what kind of compact remnant it may ultimately leave behind. But even before that final stage arrives, the star has already changed its environment. The expelled gas contains material processed inside earlier generations of stellar interiors, and it can mix with surrounding interstellar clouds rather than remaining locked inside the star. Some of the most massive stars are therefore not simply consuming fuel until an abrupt ending. They are continuously returning pieces of themselves to the galaxy while still alive. That gives stellar mass loss a quieter significance than the dramatic events usually associated with massive stars. You can look at a luminous star and imagine it as a stable object with a fixed amount of matter, but over astronomical time, its identity is leaking away into space. Millions of years can turn a star that began life extraordinarily massive into something far lighter and chemically exposed, surrounded by a vast archive made from its former outer layers. What seems permanent in a telescope image is actually an object in the process of shedding itself, reminding you that even before a star dies, the boundary between the star and the galaxy around it is never completely closed. A star can brighten dramatically because it is eating material from another star. A star can suddenly become hundreds or even thousands of times brighter without creating any new fuel of its own, simply because another star is feeding it. This happens in close binary systems, where two stars orbit so near each other that their lives can no longer be treated as separate stories. As one star ages, its outer layers may expand until some of its gas reaches a region where the companion's gravity can pull it away. The material does not usually fall directly onto the receiving star in a straight line. Because the entire system is already rotating, the stolen gas carries sideways motion and often forms a rapidly moving disk around the companion before spiraling inward. That journey can release an extraordinary amount of energy. Gas closer to the receiving star moves faster than gas farther out, creating turbulence, compression, shocks, and heating that can raise parts of the flow to extremely high temperatures. The light you observe may therefore come not mainly from the surface of either star, but from material caught between them, gradually losing orbital energy as it falls deeper into the companion's gravitational influence. In some systems, the receiving object is a normal star. In others, it is a compact stellar remnant, where the energy released per kilogram of falling gas can be far greater. This can make an otherwise unremarkable binary suddenly flare in visible light, ultraviolet, or X-rays. The brightness may also change dramatically over time because the feeding process is rarely perfectly steady. Material can accumulate in the surrounding disk faster than it moves inward, allowing the disk to store mass for weeks, months, or years. Eventually, its internal state can change, causing matter to rush inward more efficiently and producing an outburst. To someone watching from Earth, the system may brighten rapidly and then slowly fade as the disk empties, even though neither star has exploded. In other binaries, the flow can strike the receiving star or its surrounding disk at a particular location, creating a persistent hotspot that rotates through view as the stars orbit. Astronomers can use these changing brightness patterns to reconstruct an interaction they cannot spatially resolve. A rise in ultraviolet light can reveal hotter accreting material. X-rays can indicate gas reaching an especially deep gravitational environment, and repeating changes in brightness can expose the orbital period of the two stars. This means that eating is more than a dramatic metaphor. Matter really is being transferred from one star to another, and the energy released during that transfer can temporarily dominate what the entire system looks like. Yet the process also challenges the idea that a star's brightness tells you only what is happening inside that star. In an interacting binary, luminosity can be partly external. A star may shine more fiercely because material born somewhere else is arriving at its doorstep. The light becomes a record of exchange rather than isolation. Two stars that formed as companions can spend millions or billions of years quietly changing each other. And when one finally begins giving its atmosphere away, the system reveals something easy to forget when you look at separate points of light in the sky. Some stars do not evolve alone. Their brightness, mass, and future can depend on what another star is willing or forced to surrender. Some binary stars exchange matter until one of them explodes. Sometimes the star that eventually explodes has already been radically transformed by its companion long before the final moment arrives. In a close binary system, the two stars may begin life with different masses, and therefore age at different rates. The initially heavier star usually evolves first, expanding after much of the hydrogen in its core has been consumed. If the companion is close enough, the expanding star can reach a gravitational boundary beyond which its outer gas is more strongly guided toward the other star than back toward itself. Material then begins crossing the gap between them, a process known as mass transfer. What happens next can rewrite the evolution of both stars. The donor may lose much of its hydrogen-rich envelope, exposing hotter inner layers that would normally remain buried, while the receiving star gains fresh material and can become more massive, hotter, and apparently younger than its companion. This creates a strange reversal. The star that was originally the larger one can end up becoming the lighter member of the pair because it has given away so much of itself. The orbital relationship can change at the same time. Moving mass also moves angular momentum, so the distance between the stars may grow or shrink depending on how the transfer proceeds and whether some material escapes the system entirely. If the interaction becomes unstable, the expanded atmosphere of one star can even engulf both stellar cores inside a shared envelope of gas. Drag within that envelope causes the two cores to spiral closer together, while energy from their motion helps push gas away. Whether the stars eventually separate again or continue toward a merger depends on details astronomers are still working to understand. For massive stars, all of this matters profoundly when one companion finally reaches core collapse. A star stripped of most of its hydrogen by its partner will not produce the same kind of explosion signature as an otherwise similar star that kept its envelope. Its supernova may show little or no hydrogen because the missing material was removed long before the explosion. This is one reason binary interaction has become central to modern models of stellar death. The spectrum of an exploding star can contain information not only about the star's interior, but about years or centuries of interaction with a companion. The companion may survive the explosion. suddenly finding itself orbiting a compact remnant, or, if enough mass is lost and the gravitational balance changes sharply, flying away as a runaway star. It may also bear chemical or structural evidence of what happened nearby. None of this means every close binary inevitably ends in an explosion caused by mass exchange. The explosion ultimately comes from the internal evolution of the massive star, but the companion can determine what that star looks like when the end arrives, how much material surrounds it, and what kind of event astronomers observe. That distinction is important. Binary stars are not merely two independent clocks ticking beside each other until one reaches zero. They can steal mass, expose hidden layers, alter each other's rotation, change their separation, and transform the circumstances of stellar death. By the time one finally explodes, the star may be almost unrecognizable compared with the object that originally formed. And perhaps that is what makes close binaries so revealing. A star's destiny is not always written only by the mass it was born with. Sometimes its final form is negotiated over millions of years with another star orbiting beside it. A white dwarf can explode after stealing too much matter from a companion. Chi. Dead star can spend millions of years quietly taking material from a living companion until one day the theft changes from a slow transfer into the destruction of the entire star. One possible route to a Type Ia supernova begins with a white dwarf in a close binary system, often drawing gas from a companion that has expanded enough for some of its outer material to cross toward the compact remnant. The white dwarf is no longer producing energy through ordinary stellar fusion, but the incoming gas can gradually increase its mass and alter the conditions deep inside it. This is where the story becomes very different from a normal stellar explosion. A massive living star can collapse when it can no longer support its own core, but a carbon-rich white dwarf can instead be destroyed by runaway nuclear burning. As its mass and internal pressure rise, the central regions become hotter and denser. Under the right conditions, carbon fusion begins to accelerate. Normally, heating a gas makes it expand, and that expansion can cool it, providing a kind of natural break. Dense white dwarf matter behaves differently enough that the first increase in nuclear heating may not immediately produce the expansion needed to shut the reaction down. More burning creates more heat. More heat accelerates the burning, and within a short time the process runs away. A flame begins moving through the star, converting carbon and oxygen into heavier nuclei and releasing an enormous amount of energy. Scientists are still working out exactly how this burning front behaves in different explosions. Whether it begins relatively slowly, later transitions into a faster detonation, or follows another route, but the result can be catastrophic. The energy released becomes sufficient to unbind the white dwarf completely. There may be no surviving stellar core left at the center. The star is torn apart, and its material expands outward at thousands of kilometers per second. This is also why saying that a white dwarf simply reaches one exact mass and explodes is too neat. Some Type Ia supernovae may indeed involve a white dwarf gaining material from a normal companion, while others may involve two white dwarfs merging, and observations suggest nature may use more than one path to produce explosions that fall into the same broad category. In accreting systems, the type of incoming material and the rate at which it arrives can also change the outcome. Hydrogen or helium may ignite near the surface in smaller eruptions without destroying the star, while under other conditions, a helium detonation might help trigger deeper carbon burning before the white dwarf reaches the traditionally quoted maximum mass. What astronomers care about is not merely the dramatic destruction, because these explosions have an unusual scientific gift. Many Type Ia supernovae reach broadly similar intrinsic brightnesses after their light curves are carefully corrected. That allows astronomers to compare how bright the explosion appears with how bright it should be and estimate the distance to the host galaxy. Measurements of such supernovae helped reveal that the expansion of the universe is accelerating, so an unstable partnership between two stars can eventually become a tool for measuring the cosmos itself. The irony is difficult to miss. A white dwarf begins as the quiet remnant of a star whose normal life is already over, spends ages gathering material almost invisibly, and then can become visible across an enormous fraction of the universe, because the matter it accumulated finally pushes its internal nuclear conditions past a point from which there is no gentle return. The companion does not simply make the dead star heavier. It can provide the final ingredient that turns a long stellar afterlife into one last thermonuclear event, reminding you that even after a star appears finished, its surroundings can still rewrite the ending. A neutron-star collision can produce both gravitational waves and light. In 2017, the same cosmic collision reached humanity in two fundamentally different ways. First as a tremor in spacetime, and less than 2 seconds later as a flash of gamma rays. That event transformed neutron star mergers from objects scientists could mostly model into laboratories they could observe with several completely different kinds of instruments at once. Two neutron stars had been orbiting one another and gradually approaching until they finally merged. But unlike a collision between two black holes, this system contained enormous amounts of actual matter capable of being heated, torn away, accelerated, and made luminous. The approaching stars produced gravitational waves, allowing detectors on Earth to follow the final part of their inward spiral, even before telescopes knew exactly where to look. Then came a short burst of gamma rays, followed by visible and infrared light that changed over the next several days, later accompanied by X-rays and radio emission. Instead of receiving one photograph of one explosion, astronomers received several different physical accounts of the same event. The gravitational wave signal revealed information about the masses and orbital motion of the two stars. The gamma rays pointed to an extremely fast outflow launched during or shortly after the merger. The changing visible and infrared glow revealed expanding material cooling around the source. Months of X-ray and radio observations then showed how a high-speed jet interacted with the surrounding environment. Each messenger answered a question the others could not answer alone. Even the small delay between the gravitational waves and gamma rays became scientifically powerful. Both signals had traveled for roughly 130 million years before reaching Earth, yet they arrived less than 2 seconds apart. That observation placed remarkably tight limits on any difference between the speed of gravity and the speed of light, providing a direct test of theories that attempted to modify gravity on cosmic scales. The event also solved a long-standing mystery about at least some short gamma-ray bursts by showing that neutron star mergers can produce them. And because gravitational waves provide an independent estimate of distance, while telescopes can identify the host galaxy and measure how quickly that galaxy is moving away, these mergers offer another method for studying the expansion rate of the universe. This approach is still limited by the relatively small number of well-observed events, but future detections could make it increasingly useful. The collision also allowed scientists to probe something impossible to place inside any laboratory: how neutron star matter behaves when subjected to the final moments of an inspiral. The precise shape of the gravitational wave signal is influenced slightly by how easily each star is deformed by its companion's gravity, so better measurements can help researchers constrain the properties of matter at extraordinary density. After the stars meet, the outcome is not always known immediately, depending on their combined mass and internal physics. The merger may briefly create an extremely massive neutron star before collapsing further, or it may form a black hole more quickly. The light and gravitational signals can contain clues about which path occurred. This is why the event mattered beyond its spectacle. Astronomy had traditionally relied overwhelmingly on electromagnetic radiation, visible light, radio waves, X-rays, gamma rays, and other wavelengths that are all different forms of the same basic messenger. Gravitational waves added something genuinely new. Now the same catastrophe could be studied through both the motion of space-time and the behavior of matter. It is a little like learning about a distant storm by seeing the lightning and feeling the ground shake beneath you, with each sensation revealing a different part of the event. A neutron star merger therefore does more than produce several kinds of signals. It demonstrates that the universe can tell the same story through independent channels. And when those channels arrive together, details that would remain ambiguous in either one alone can suddenly become clear. The universe contains objects so dense that atoms cannot survive inside them. An atom feels almost indestructible in everyday life, yet there are places in the universe where gravity compresses matter so violently that the familiar architecture of atoms simply cannot continue to exist. Inside a neutron star, the pressure rises far beyond anything found in planets, ordinary stars, or laboratories on Earth, and as you descend beneath the surface, matter passes through a sequence of increasingly unfamiliar states. Near the outer crust, atoms can still exist in a distorted form. Heavy nuclei sit in a dense sea of electrons, packed far more tightly than any normal material. Go deeper, however, and the pressure becomes so great that some electrons are forced into atomic nuclei, where they combine with protons and help create neutrons. Eventually, neutrons begin leaking out of nuclei altogether, producing a strange mixture of neutron-rich nuclei, free neutrons, and electrons. Deeper still, even those nuclei may lose their familiar identity. The material becomes so compressed that talking about separate atoms no longer makes sense, because the distances and structures that define ordinary atomic matter have been erased by pressure. Some models predict bizarre transitional arrangements in the inner crust, where nuclear material may organize into sheets, rods, or other shapes sometimes nicknamed nuclear pasta. The name sounds playful, but the physics behind it is serious. The attractive nuclear force and the repulsion between positively charged particles compete under extreme compression, potentially creating structures unlike any material you could hold. Farther inward lies the core, and here the uncertainty becomes even more interesting. Scientists know that the density becomes comparable to, and may exceed, the density inside atomic nuclei, but they still do not know exactly what form the matter takes. It may consist largely of neutrons with smaller populations of protons and electrons, yet more exotic possibilities have been proposed, including unusual particle states or forms of matter in which the basic components of protons and neutrons behave differently from anything accessible in terrestrial experiments. The important point is not that one of these ideas has already been proven, but that astronomers can test them indirectly by measuring how massive neutron stars can become, how large they are, how they respond to rotation, and how they deform under gravity. Different kinds of dense matter produce slightly different relationships between a star's mass and size, so each precise observation narrows the range of possibilities. This turns a neutron star into something more than a crushed stellar remnant. It becomes a natural experiment in what happens when matter is pushed beyond the atomic world you know. On Earth, nearly everything around you, from air to stone to your own body, depends on atoms maintaining recognizable structures. Inside these objects, that familiar order is gone. Electrons no longer occupy ordinary atomic arrangements. Nuclei become increasingly unstable as independent structures, and matter enters regimes where our everyday language starts to fail. You are left with a profound reversal of perspective. Atoms seem fundamental because they dominate your world. But the universe contains environments where atoms are only a temporary arrangement, stable under gentle conditions and erased when gravity pushes matter into a deeper state. Gravity can become strong, enough to stretch matter into long streams. There is a point where gravity stops behaving like a simple downward pull and begins pulling different parts of the same object in different directions strongly enough to change its shape. This happens because gravity is not equally strong across an extended body. If your feet are closer to a compact, massive object than your head, your feet feel a slightly stronger gravitational attraction. Around Earth, that difference is tiny, so you never notice it. But near something extremely compact, the difference can become enormous over only a few meters. The result is a tidal force. One end of an object is pulled more strongly than the other, while sideways directions can be squeezed inward. If the gradient becomes severe enough, a falling object can be stretched lengthwise and compressed across its width. producing the famous process informally called spaghettification. The unsettling part is that you would not need to collide with anything for this to happen. There is no solid wall responsible for the stretching. The distortion comes entirely from the changing strength of gravity from one point in your body to another. Molecules are held together by electromagnetic forces, tissues by molecular bonds, planets by their own gravity, and every structure has a point beyond which those internal forces can no longer resist an external tidal gradient. Once that threshold is crossed, a coherent object begins turning into a stream of material. The exact experience depends strongly on the mass of the compact object. Near a smaller black hole, tidal forces can become lethal well before you reach the boundary beyond which escape is impossible, because the gravitational field changes extremely rapidly over a short distance. Around an enormous black hole, however, the gradient at that boundary can be much gentler. In principle, you could cross it without immediately being torn apart, only encountering catastrophic tidal stretching deeper inside. This may seem backwards. You might expect the larger black hole to be more destructive at every distance, but tidal forces depend not only on how strong gravity is, but on how rapidly that strength changes across your body. That distinction is crucial. Uniform acceleration does not tear you apart. Differences in acceleration do. Astronauts in orbit feel weightless, even though Earth's gravity is still acting strongly on them, because they and their spacecraft are falling together. Stretching begins when different parts can no longer share nearly the same fall. The same principle operates on much larger scales. Moons can be pulled into elongated shapes by planets, oceans rise and fall under lunar tides, and close stellar encounters can distort entire stars. Near an extremely compact object, however, the same physics is amplified until solid matter, gas, and eventually even tightly bound structures can be forced into narrow streams. At first, this sounds like one more dramatic property of extreme gravity, but it reveals something deeper about what gravity really does. Gravity does not merely move objects from one place to another, it can act differently across the dimensions of a single object, testing whether that object can remain one thing at all. A body feels unified because the forces holding its parts together normally dominate over differences in the surrounding gravitational field. Change the environment enough, and that unity becomes conditional. What you call an object, a rock, a spacecraft, a body, is only a temporary agreement among its parts, and sufficiently uneven gravity can eventually pull that agreement apart. Light can orbit a black hole before escaping toward us. There is a region around a black hole where light can do something that sounds almost contradictory. Instead of immediately escaping or falling inward, it can travel around the black hole in a circle. This happens near what physicists call the photon sphere, a zone outside the event horizon where gravity has curved space-time so strongly that certain paths taken by light bend all the way around the black hole. But the word orbit needs to be handled carefully, because this is nothing like a planet settling into a comfortable path around a star. A photon orbit is extraordinarily unstable. If the light travels along exactly the right trajectory, it can circle the black hole, but the slightest change can decide its fate. One path sends it inward, where it eventually crosses the event horizon and can never return. Another sends it outward, allowing the photon to escape and perhaps travel across the universe until it enters a telescope. This means some of the light reaching you from the immediate environment of a black hole may have taken an astonishing detour first. A photon emitted by hot material nearby can swing around the black hole once before escaping. Another may circle twice. A still more precisely aimed photon can loop around several times before finally breaking free. Each extra circuit creates another highly distorted image of the glowing material surrounding the black hole, producing a sequence of increasingly narrow and faint rings near the edge of the black hole's shadow. The reason these rings become so thin is that the required paths become incredibly precise. Light that begins only slightly farther to one side escapes without making as many turns, while light shifted slightly toward the other side is captured. The photons that complete many circuits therefore occupy an increasingly narrow range of possible trajectories. This also means that looking toward the photon sphere is, in principle, looking at multiple histories of the same environment. Light that reached you directly followed a shorter route, while light that circled the black hole first traveled farther and therefore arrives later. You are not seeing several different disks occupying the same place. You are receiving different versions of the same surrounding material carried along different paths through curved spacetime. Near a black hole, even the far side of a glowing disk can become visible because its light can be bent upward, over, or around the black hole before reaching you. The result is why realistic black hole simulations often look strangely folded, with parts of the disk appearing above and below the dark center, even though the physical disk itself may be relatively flat. None of this means light is slowing down or being physically dragged like a marble rolling around a funnel. Locally, light still travels at the same fundamental speed. What has changed is the geometry through which it moves. The straightest available route through strongly curved spacetime can look profoundly curved when viewed from far away. And that gives the photon sphere a special place in black hole physics. It is not a solid shell, not a luminous surface, and not a safe parking orbit for light. It is a precarious boundary of trajectories, where an almost imperceptible difference determines whether a photon disappears forever or eventually escapes. So when a telescope collects radiation from the edge of a black hole's darkness, some of those photons may be carrying a much stranger story than a simple journey from source to observer. They may have traveled around an object that cannot itself be seen, repeatedly passing through nearly the same region before finally finding a route outward. A black hole does not need to emit light to reshape what you see. It can take light produced nearby, fold its path around itself, and send it towards you only after that light has nearly been lost. The shadow of a black hole is larger than the black hole's event horizon. The famous dark circle in a black hole image is not the event horizon itself, and understanding that single detail changes what those images actually mean. The event horizon is the true boundary beyond which outward escape becomes impossible, but it does not have a glowing edge that a telescope can photograph directly. What telescopes can detect is radiation from material outside the black hole. And against that luminous background, the black hole creates a dark region called its shadow. The shadow appears larger than the event horizon because light does not travel past the black hole along ordinary straight-looking paths. Well, outside the horizon, strong gravity can already bend incoming photons so severely that they are captured instead of reaching the observer. Imagine tracing every ray of light backward from your telescope toward the black hole. Some rays pass far enough away that they are merely deflected and eventually connect to glowing material behind or beside the black hole. Others pass too close, become trapped, and terminate at the event horizon. The directions on your sky corresponding to all those captured rays form the dark shadow. The edge of that darkness therefore marks a critical family of light paths, not the physical location of the horizon itself. For an idealized, non-spinning black hole, this effect makes the apparent shadow roughly 2.5 times wider than the event horizon diameter when viewed from far away, although rotation, viewing angle, and the surrounding emitting material complicate the exact appearance of real systems. This distinction became especially important when the Event Horizon Telescope produced the first famous images of supermassive black holes. The bright orange-looking ring in those reconstructed images is not a photograph of a glowing event horizon, and the dark center is not simply a direct picture of the physical hole cut out at its true size. The bright structure comes from radiation produced by hot material around the black hole, and then dramatically reshaped by relativity, while the central depression corresponds to the shadow created because a range of light trajectories never reach us. The event horizon lies deeper inside that apparent darkness. This is why the shadow is so scientifically useful. Its size is tied strongly to the black hole's mass, and its overall shape is predicted by general relativity to remain close to circular under ordinary astrophysical conditions. By measuring the ring and shadow, Astronomers can therefore test whether observations match the geometry predicted for an actual black hole rather than some alternative compact object. The agreement has so far been remarkably strong. But there is another reason the shadow is conceptually important. It demonstrates that an astronomical image does not always show an object's physical boundary. You are seeing the behavior of light around that boundary. A photograph of the moon shows sunlight reflected from a fairly definite rocky surface. A black hole image is fundamentally different. There is no surface reflecting light towards you, and nothing from inside the horizon is being photographed. Instead, the black hole announces its presence through missing photons, through paths that could have brought radiation to your telescope, but were diverted into darkness instead. The larger silhouette is therefore created by gravity before the light ever reaches the horizon. In a sense, the black hole looks bigger because its influence on visibility begins outside the place from which escape becomes impossible. That may be the most useful way to interpret the dark center of a black hole image. You are not looking directly at the boundary of the object. You are looking at the region of the sky from which light has been systematically removed by the geometry surrounding it. The horizon itself remains hidden inside, smaller than the darkness that tells you it is there. Black holes can grow to billions of solar masses. A black hole can begin as the remnant of a single star and, given enough time and the right environment, become so massive that millions or even billions of suns would be required to equal it. These giants are usually found in the centers of galaxies, where gas, stars, and other black holes are concentrated closely enough for growth to continue over immense periods. But a black hole does not simply vacuum up everything around it. Most material in a galaxy has too much sideways motion to fall straight in, so gas often settles into orbit first, gradually losing energy and moving inward through a disk. When fresh gas reaches the central region of a galaxy, especially after galaxies interact or merge, the black hole can enter a period of rapid feeding. This sounds like unlimited growth, yet there is a natural complication. The infalling gas becomes extremely bright before it disappears. Radiation from that hot material pushes outward on surrounding gas, making it harder for more matter to continue falling inward. In many systems, this creates a kind of self-regulation in which the black hole's own feeding activity begins to interfere with its future supply. Powerful winds and jets can also push gas away from the galactic center, sometimes reducing the amount available for both black hole growth and new star formation. So becoming a billion solar mass black hole is not simply a matter of waiting beside an endless reservoir. The environment has to keep delivering material, despite the energy released by previous feeding episodes. Mergers offer another route. When two galaxies combine, the massive black holes that occupied their centers can eventually sink toward the middle of the new system and, under the right circumstances, merge into a larger object. Repeating this process across cosmic history can help build increasingly massive black holes, especially in the centers of large galaxies and galaxy clusters. Yet even among these giants there is enormous variety. Some central black holes are relatively quiet because little gas is currently reaching them, while others are actively feeding and can become among the most luminous objects visible across the universe. The mass of the black hole itself does not determine how bright the system must look at any given moment. A billion solar mass black hole can be nearly dormant if starved of fuel, while a smaller one may shine intensely if surrounded by abundant gas. Astronomers estimate these enormous masses indirectly by watching how fast nearby stars or gas move, by studying the light from rapidly orbiting material, or by measuring how the central object affects its surroundings. The numbers become difficult to picture because the black hole's mass can rival a noticeable fraction of all the stars in a small galaxy while remaining concentrated in a region tiny compared with the galaxy itself. And this creates one of the most important relationships in modern astronomy. The biggest black holes and the galaxies around them appear to have influenced each other's growth. The black hole depends on the galaxy to supply fuel, while the energy released during feeding can alter the galaxy's gas and future evolution. A supermassive black hole is therefore not simply a giant object sitting passively in the middle of a galaxy. It is part of a long exchange between gravity, gas, stars, mergers, and feedback that unfolds over billions of years. When you hear that a black hole contains several billion solar masses, the truly remarkable fact is not only that so much mass can exist in one place, it is that the universe had to repeatedly deliver, concentrate, and retain that material while the growing black hole was continuously making its own environment harder to feed from. Some enormous black holes already existed when the universe was very young. The real mystery is not that the universe can make enormous black holes, but that it seems to have made some of them astonishingly early. Astronomers have found actively feeding black holes containing hundreds of millions or even billions of solar masses at distances so great that we see them as they existed when the universe was only a small fraction of its current age. In some cases, within the first several 100 million years after the Big Bang. That creates a serious timing problem. A black hole cannot simply begin with billions of solar masses. It needs a starting seed and then enough opportunities to grow. If the seed came from the collapse of one of the first massive stars, it may have started with only tens or perhaps hundreds of solar masses. From there, reaching a billion requires repeated multiplication of its mass. But feeding cannot always proceed arbitrarily fast, because the radiation produced by incoming matter can push new material away and slow further growth. Under fairly steady conditions, a black hole can grow exponentially, but even exponential growth needs time, and the early universe did not provide much of it before some of these enormous objects were already shining. This has led researchers to consider several possible solutions. One is that the first black hole seeds were much more massive than ordinary stellar remnants. In certain young galaxies, enormous clouds of primordial gas may have collapsed almost directly into black holes weighing thousands or tens of thousands of suns, giving later growth a considerable head start. Another possibility is that early black holes sometimes fed faster than the simple long-term limits normally assumed, especially in dense environments where huge quantities of gas were driven toward the center. Short periods of unusually rapid growth could help explain how a relatively modest seed became enormous before the universe was even a billion years old. Mergers between early black holes may have contributed as well, although simply combining objects is unlikely to remove the need for substantial gas accretion. The surroundings of these young black holes make the problem even more interesting. The first galaxies were themselves still assembling from gas, smaller systems, and dark matter. So black hole growth and galaxy formation may have occurred almost simultaneously rather than in the neat sequence you might imagine, where a mature galaxy forms first and then slowly builds its central black hole. In some cases, the central black hole may have grown extraordinarily quickly while the host galaxy was still young and chaotic. Astronomers study the light from these distant systems to estimate black hole masses, chemical composition, gas motion, and feeding rates. But every observation is difficult because the light has traveled for more than 13 billion years and reaches us faint and strongly shifted toward longer wavelengths. New infrared observations are now revealing increasingly early active black holes, forcing scientists to refine models of how quickly the first massive structures could form. None of this means our understanding of black holes has collapsed. It means the initial conditions of the early universe may have been unusually favorable for rapid growth in ways that are still being worked out. And that is what makes these ancient giants so important. When you look at one, you are seeing more than a distant black hole. You are seeing a deadline imposed on cosmic history. By the moment that light left its galaxy, nature had already found a way to assemble an enormous concentration of mass, feed it efficiently, and make it shine while the universe itself was still young. The question is no longer whether giant black holes can exist. We know they can. The harder question is how the universe learned to build them so quickly. Quasars can shine brighter than entire galaxies, from a region smaller than a solar system. Imagine discovering a point of light so distant that its photons have crossed most of the observable universe, then realizing that this tiny-looking source can produce more light than the hundreds of billions of stars in the galaxy surrounding it. That is the extraordinary reality of a quasar. A quasar is not a special type of star, nor is the black hole at its center itself glowing. What you are seeing is an extremely active galactic nucleus, where enormous quantities of matter are being transformed into radiation in the immediate environment of a supermassive black hole. The truly revealing clue is not just how bright quasars are, but how quickly some of them change. Astronomers have watched their brightness fluctuate over days, hours, and in some cases even shorter intervals at particular wavelengths. That variation places a limit on the size of the region producing the changing light, because a source cannot coordinate a brightness change across a region faster than light can travel through it. If a quasar noticeably changes over a short time, at least some of its emission must therefore come from a remarkably compact area, sometimes comparable to the scale of a planetary system, rather than the vast dimensions of an entire galaxy. Yet from that small central region can emerge a luminosity that overwhelms the combined starlight around it. The reason is efficiency. Ordinary stars shine because nuclear fusion gradually converts a small fraction of their mass into energy. Near a supermassive black hole, matter falling into a deep gravitational environment can release a much larger fraction of its available energy before disappearing. Gas moving inward becomes compressed, turbulent, magnetized, and extremely hot, producing radiation across a huge range of wavelengths, from infrared and visible light to ultraviolet and X-rays. Surrounding this compact central engine are larger regions of rapidly moving gas, whose atoms leave recognizable signatures in the quasar's spectrum. Those spectral lines can be enormously broadened, because the gas is traveling at thousands of kilometers per second, allowing astronomers to estimate how quickly material is moving, even when the entire central system is far too distant to resolve directly. Quasars also gave astronomy an early lesson in how deceptive appearance can be. Many looked almost star-like in old telescope images, yet their spectra showed that they were located at enormous cosmological distances. If something so far away still appeared extremely bright, its true energy output had to be staggering. Today, quasars are useful not only because they are powerful, but because their brightness allows them to act as background beacons. Their light can pass through otherwise difficult to detect gas between galaxies, leaving absorption patterns that reveal material spread across billions of light years. In that way, a quasar can tell you about regions of the universe nowhere near the quasar itself. And there is a final correction that keeps the picture grounded. When people say a quasar shines from a region smaller than a solar system, they do not mean every part of the quasar is squeezed inside the orbit of Earth. Different wavelengths come from different scales, and some surrounding structures extend far beyond the central light-producing zone. The astonishing fact is that the core responsible for much of the rapidly varying energy can be extraordinarily compact compared with the galaxy hosting it. A galaxy may span 100,000 light-years, yet for a period of cosmic history, its appearance can be dominated by activity taking place in a region almost unimaginably smaller. It is one of the clearest examples of a lesson the universe repeats in unexpected ways. Physical size and influence are not always proportional, and sometimes the brightest object you can see is powered by something occupying only the smallest fraction of the system around it. A supermassive black hole can launch jets thousands of light years into space. Some galaxies contain structures so long that they extend far beyond the visible region where most of their stars live. Yet those enormous structures can begin near a central black hole occupying only a tiny fraction of the galaxy's size. They are astrophysical jets, narrow streams of energized particles and magnetic fields launched from the environment surrounding actively feeding supermassive black holes. The black hole itself is not firing material back out from inside the event horizon. Anything that crosses that boundary cannot return. The jet is produced outside it, where rapidly moving plasma and powerful magnetic fields interact with matter orbiting the central object. As material circulates near the black hole, magnetic fields can become twisted, stretched, and organized into large-scale structures. Under the right conditions, these fields can redirect part of the available energy away from the crowded central region and accelerate charged particles outward along the black hole's rotational axis. Instead of spreading equally in all directions, the flow becomes tightly focused, forming two opposing beams that can travel far beyond the galaxy's center. The most astonishing part is how well a jet can remain collimated. You might expect a stream of hot plasma to spread outward rapidly, like smoke from a fire. Yet some cosmic jets stay comparatively narrow across thousands, or even hundreds of thousands of light years. Magnetic fields appear to play a major role in keeping the flow organized, while the pressure and density of the surrounding galactic environment also influence its shape. As the jet travels, it interacts with gas between the stars, and eventually with the much thinner material between galaxies. These collisions can produce bright knots, shocks, and enormous radio-emitting lobes where particles are accelerated to extreme energies. Astronomers often detect the structures most clearly at radio wavelengths because fast-moving charged particles spiraling through magnetic fields produce a distinctive form of radiation. That signal allows researchers to trace a jet long after it has left the immediate neighborhood of the black hole. Jets also show that a central black hole can affect regions vastly larger than itself without ever physically traveling there. Energy carried outward can heat surrounding gas, stir the atmosphere of a galaxy cluster, carve cavities in hot gas, and influence whether material can cool enough to form new stars. This process is one reason astronomers take black hole feedback seriously when trying to understand how galaxies evolve. A supermassive black hole may occupy a minuscule central volume, but the energy associated with its activity can regulate conditions across a region containing billions of stars. Not every actively feeding black hole produces the same kind of enormous jet, and scientists are still investigating why some systems become dramatically radio bright while others do not. The strength and arrangement of magnetic fields, the black hole's rotation, the rate at which matter arrives, and the history of the surrounding galaxy may all matter. The jet itself can also change with time, so the giant structures visible today may preserve evidence of earlier periods when the central engine was more active than it is now. This turns a jet into something like a fossilized record of galactic activity written across space. The central region may brighten and fade on relatively short astronomical timescales, while particles already launched continue traveling outward and interacting with their surroundings far away. So when you see a jet stretching for thousands of light years, you are not looking at a single rigid object attached to a black hole. You are looking at energy being transported across a galaxy over immense spans of time, guided by magnetic fields, and carried by particles moving at extraordinary speeds. A black hole may be famous for what it prevents from escaping, but some of the largest structures associated with it are created by energy launched outward before matter ever crosses the point of no return. Some cosmic jets appear to move faster than light without actually breaking relativity. A telescope can watch a bright knot in a distant cosmic jet cross the sky so quickly that, if you calculate its apparent speed in the obvious way, the answer can come out faster than light. That sounds like a direct violation of relativity, but nothing in the jet actually has to outrun light for the illusion to appear. The trick comes from combining two things. The material is already moving extraordinarily close to light speed, and the jet is aimed partly toward you rather than traveling sideways across your view. Imagine a bright clump moving forward through the jet and emitting one flash of light, then moving much closer to Earth before emitting another. The first flash begins its journey while the clump is farther away. By the time the second flash is emitted, the clump has covered an enormous distance toward you, so that second light signal has a shorter journey to make. As a result, the time separating the arrival of the two flashes at Earth can be much shorter than the time separating their emission at the source. Meanwhile, you also see the clump shift sideways across the sky. Divide that apparent sideways distance by the unusually compressed arrival time, and the calculated motion can look faster than light. What you are measuring is therefore not the true speed of the material through local space, but a projection created by geometry and light travel time. This phenomenon is called apparent superluminal motion, and it has been observed in jets associated with active galaxies and other energetic systems. It becomes most dramatic when the jet points only a small angle away from our line of sight, and its material is traveling extremely close to light speed. The same geometry produces another important effect. Radiation from material moving toward us can appear dramatically brighter than radiation from material moving away. Because the particles are moving so rapidly, their emission becomes concentrated in the forward direction, making one jet look brilliant, while its partner on the opposite side may appear weak or even invisible. Astronomers can use the apparent motion and brightness of these features to estimate the true speed and orientation of the flow, turning what initially looks like a contradiction into a measuring tool. There is another subtle point worth keeping clear. Relativity does not say that nothing can ever appear to move faster than light. It says that matter, information, and locally measurable signals cannot travel through space faster than light in the usual sense. An apparent position on the sky is not an object carrying information sideways at the calculated superluminal speed. The actual particles remain below the limit. This is why you do not need new physics to explain what telescopes see. You need only to remember that astronomy never shows you events exactly when they happen. Every image is assembled from photons that left different locations at different times, and then spent years, thousands of years, or billions of years traveling toward you. When the source itself is moving almost as fast as those photons, the difference between emission time and arrival time becomes impossible to ignore. What looks like the universe breaking its own speed limit is really the universe demonstrating how carefully that limit works. Your eyes instinctively reconstruct motion as though the scene were happening at one shared moment. But the light reaching you has carried a more complicated history. Sometimes the strangest apparent violation of a physical law becomes, once you understand the geometry, one of its most elegant confirmations. Entire galaxies can collide without most stars ever touching. When two galaxies crash into each other, billions of stars can pass through the same enormous collision without a single star ever physically striking another. The reason becomes clear only when you stop imagining a galaxy as a solid swarm and begin thinking about how much empty space exists between its stars. The Sun is enormous compared with Earth, yet the nearest star beyond our solar system is more than 4 light-years away. That pattern repeats across a galaxy. Stars occupy tiny volumes compared with the distances separating them. So when two galaxies overlap, their stellar populations mostly thread through one another, like two clouds of widely scattered grains passing through the same region. Direct star-on-star collisions are possible in principle, especially in unusually dense environments, but during a typical galaxy merger, they are extremely rare. Gravity, however, does not require physical contact. As the galaxies approach, each one pulls on the other's stars, gas and dark matter over vast distances. Their original shapes begin to distort. Long tidal tails can be drawn outward. Some stars are sent onto new orbits, and entire spiral patterns may be stretched or disrupted. The gas behaves very differently from the stars because gas clouds are extended and can actually collide. When clouds from the two galaxies encounter one another, they can be compressed, shocked, and rearranged, sometimes creating conditions that encourage intense episodes of new star formation. A galaxy merger can therefore produce spectacular bursts of stellar birth, even though the old stars themselves are mostly passing harmlessly by one another. The process is also much slower than the word collision suggests. Galaxies do not hit once and instantly combine. They can pass through each other, separate again, then fall back together because their mutual gravity has changed their motion. Each passage removes some of the organized orbital energy, and over hundreds of millions or even billions of years, the two systems can eventually settle into a single larger galaxy. During that time, the distribution of stars can become completely reorganized. Two beautiful spirals may ultimately produce a smoother, more rounded galaxy whose stars follow complicated orbits rather than remaining in thin, ordered disks. Their invisible dark matter halos interact gravitationally as well, becoming part of the final combined structure. If both galaxies contain massive objects at their centers, those central regions can eventually move toward one another as the merger progresses, although that later evolution occurs on its own long time scale. What makes all of this so useful to astronomers is that galaxy mergers are not rare accidents disconnected from normal cosmic history. They are one of the main ways galaxies grow and change. The large galaxies you see today were not necessarily born at their present size. Many were assembled gradually through repeated encounters with smaller systems. Even the appearance of a galaxy can preserve evidence of old mergers in faint stellar streams, unusual shells, warped disks, or populations of stars moving in unexpected directions. So when you see two galaxies apparently crashing together in a telescope image, the violence is real, but it is not happening in the way your intuition first suggests. The galaxies are being transformed by gravity on a scale so large that individual stars barely notice one another passing. It is a collision where almost nothing collides, a merger driven less by impact than by the slow rewriting of billions of orbits. And that may be the most revealing part. On cosmic scales, two structures can pass directly through each other and still emerge permanently changed, because gravity does not need things to touch in order to rearrange their future. The Milky Way is already interacting with other galaxies. You do not have to wait billions of years for the Milky Way to meet another galaxy, because the interaction is already happening around you on a scale so large that the night sky barely reveals it. Our galaxy is surrounded by smaller companion galaxies whose gravity has been pulling on the Milky Way and being pulled in return for immense stretches of time. And some of those companions are already being reshaped by the encounter. One of the clearest examples is the Sagittarius Dwarf galaxy, a small system that has repeatedly passed through the Milky Way and is now being torn apart. As it moves through our galaxy's gravitational field, stars are stripped from it and stretched into enormous streams that wrap around the Milky Way like faint ribbons. Those streams are not random decorations. Their positions and motions preserve a record of the dwarf galaxy's orbit, allowing astronomers to reconstruct encounters that began long before humans existed. The Milky Way is also interacting with the Large and Small Magellanic Clouds, two prominent satellite galaxies visible from the southern hemisphere. Between and behind them lies a vast trail of gas known as the Magellanic Stream, extending across a huge portion of the sky. Much of this material appears to have been pulled and removed during the complicated gravitational interaction between the two clouds and the Milky Way, although astronomers are still refining the exact history of how the stream formed. These encounters can affect more than the satellites themselves. A passing companion can disturb the Milky Way's disk, helping create ripples, warps, and unusual motions among stars. Astronomers have found that the outer disk is not a perfectly flat, quiet structure. It bends and vibrates, and part of that behavior may reflect repeated gravitational disturbances from nearby satellite galaxies. Even the Milky Way's surrounding halo can respond. A sufficiently massive companion moving through the halo creates a gravitational wake, a region where matter is redistributed behind its path, which can subtly influence the motions of other objects. This means the galaxy you live in is not an isolated island maintaining the same shape forever. It is constantly exchanging gravitational influence with its surroundings, absorbing smaller systems, stripping stars and gas from them, and carrying evidence of ancient encounters in the motions of stars scattered through its halo. Some stars now considered members of the Milky Way were probably born in galaxies that no longer exist as independent systems. Their chemistry and unusual orbits can expose their foreign origin, allowing astronomers to identify fragments of past galaxies long after their original structures have disappeared. Seen this way, the Milky Way is less like a finished object and more like an archaeological site still under construction. Its present form contains pieces acquired from earlier encounters, while new interactions are continuing right now. You may look up and see a calm band of starlight crossing the sky, but that apparent stillness is only a consequence of your short lifetime. On galactic timescales, the Milky Way is being tugged, warped, fed, and rearranged by companions moving through its gravitational neighborhood. The galaxy that feels permanent beneath your night sky is actually a changing structure carrying the scars and borrowed stars of other galaxies within it. Galaxies can be stripped of their gas while moving through galaxy clusters. Galaxy can enter a crowded cluster rich in cold gas and emerge millions of years later, still full of stars, but almost incapable of creating new ones. The reason is not that its existing stars are removed one by one, but that the galaxy can lose the raw material from which future stars would have formed. Large galaxy clusters are filled not only with hundreds or thousands of galaxies, but also with extremely hot, thin gas spread throughout the space between them. This gas is difficult to notice with your eyes because it is so diffuse, yet it can contain an enormous amount of matter and reach temperatures high enough to emit X-rays. When a galaxy races through this environment at hundreds or even thousands of kilometers per second, its own gas feels something similar to a powerful headwind. The stars are compact and widely separated, so they pass through largely unaffected, but the galaxy's clouds of gas present a much larger target. Pressure from the cluster environment can push against that gas strongly enough to overcome the galaxy's grip on it, peeling material away and leaving a long trail behind. Astronomers call this ram pressure stripping, and some of the most dramatic examples are known as jellyfish galaxies, because their stripped gas forms extended tails that resemble tentacles trailing behind the stellar disk. These tails are not merely empty streams. Compressed regions within them can sometimes become dense enough to form new stars, meaning a galaxy may briefly create stars inside material that is already being torn away from it. But the long-term effect is usually much less generous. Once much of the cold gas is gone, the galaxy begins running out of fuel for future star formation. Its existing hot, bright young stars eventually age and disappear, while fewer new ones replace them. Over time, the galaxy becomes redder and quieter, not because all of its stars have died, but because the stellar population is no longer being renewed at the same rate. This gives astronomers a powerful explanation for why galaxies living inside dense clusters often look different from similar galaxies in quieter environments. Location can influence evolution. A galaxy does not develop only according to what is inside it. The environment it travels through can change its future. The stripping can also occur unevenly. Gas on the leading side may be compressed first, while material farther out in the disk is easier to remove than gas held tightly near the center. Researchers can therefore study the shape of the gas tail, the locations of newly formed stars, and the remaining gas inside the galaxy to estimate which direction it is moving and how strongly the surrounding cluster is affecting it. In some cases, the stripped material stretches for tens of thousands of light years, creating a visible trail of what the galaxy is losing in real time. And this changes the meaning of a galaxy cluster. It is not simply a collection of galaxies sitting near one another like houses in a city. The space between them matters. That seemingly empty environment can exert enough pressure to rewrite a galaxy's ability to produce stars for billions of years. A galaxy may keep most of its old stellar population and still undergo a profound transformation, because the invisible material between galaxies removed the fuel for everything that would have come next. Sometimes cosmic evolution is not about destroying what already exists. It is about quietly taking away the possibility of what could have formed. Some galaxies have almost stopped making new stars. A galaxy can contain hundreds of billions of stars and still be, in an important sense, running out of future. Astronomers call such galaxies quenched when their rate of forming new stars has dropped dramatically compared with active star-forming galaxies, and the transformation is not caused by one universal mechanism. New stars require cold, dense clouds of gas that can collapse under their own gravity. So anything that removes that gas, heats it, prevents it from cooling, or stabilizes it against collapse can slowly shut down the stellar factory. Sometimes a galaxy simply uses much of its available cold gas over billions of years faster than fresh material can replace it. In other cases, gas falling toward a massive galaxy is heated to such high temperatures that it remains suspended in a hot halo, instead of cooling efficiently into the central disk. Activity around a central supermassive black hole can also inject enormous amounts of energy into surrounding gas through radiation, winds, or jets, keeping part of that material too hot or too disturbed to form stars easily. Even the structure of the galaxy can matter. A massive central bulge can alter the gravitational stability of the disk, making gas less likely to collapse into new stellar nurseries, even when some cold material remains. This is why astronomers no longer think of quenching as a simple switch that turns every galaxy off in the same way. Two galaxies can look similarly quiet today while having reached that state through very different histories. The change also leaves fingerprints in their light. Young massive stars are hot and blue, but they live only relatively short lives. If star formation declines and no new generation replaces them, the blue population disappears first, leaving behind older, cooler stars that make the galaxy look redder. This is why many quiet galaxies occupy what astronomers call the red sequence, while actively star-forming systems are often bluer. But color alone is not enough, because dust can redden a galaxy that is still forming stars. So researchers combine color with spectra, infrared observations, gas measurements, and other clues to determine whether star formation has truly slowed. Some galaxies appear to pass through an intermediate phase in which star formation is declining but has not vanished, giving astronomers a chance to study the shutdown while it is happening. Others can even restart modest star formation if fresh cold gas arrives later, showing that quenching is not always irreversible. The important idea is that a galaxy does not die when its stars disappear. Most of its stars can continue shining for billions of years after the production line has nearly stopped. What changes is the rate at which the galaxy creates replacements and new stellar systems. A quenched galaxy can therefore look enormous, bright, and perfectly alive while quietly consuming the last chapters of a much older population. And that changes the way you might think about cosmic aging. A galaxy's future is not determined only by how many stars it already contains, but by whether it can keep turning diffuse matter into new suns. When that cycle slows, the galaxy has not vanished. It has simply begun living more from memory than from renewal. Invisible dark matter appears to hold galaxies together. If you measured only the stars and gas you can see in many galaxies, their outer regions should move very differently from the way they actually do. This discrepancy became one of the strongest clues that galaxies contain far more gravitating material than their visible matter can account for. In a simple system where most of the mass is concentrated toward the center, you would expect objects farther out to orbit more slowly, much as the outer planets in our solar system move more slowly than the inner ones. But when astronomers measure the rotation of spiral galaxies, they often find that stars and gas far from the bright center continue moving at unexpectedly high speeds. The rotation curves remain roughly flat instead of falling away as visible matter alone would predict. Something additional appears to be contributing gravity well beyond the luminous disk. The leading explanation is dark matter, material that does not emit, absorb, or reflect enough light for us to see it directly, yet still contributes mass and therefore gravity. Rather than forming a thin disk like most of a galaxy's stars, dark matter is thought to surround the galaxy in a much larger, roughly spherical halo extending far beyond the visible edge. The stars you see would then occupy only the bright inner portion of a much bigger gravitational structure. This idea does more than repair rotation curves. Computer models of galaxy formation work far better when ordinary matter begins inside large concentrations of dark matter, because those invisible gravitational wells help gather gas and provide the framework within which galaxies can grow. Motions of satellite galaxies and stars far from galactic centers also point toward additional unseen mass, and independent measurements on larger scales support the same broad conclusion. Still, calling it dark matter can create the false impression that scientists know what substance is hiding there. They do not. The name describes what the material appears to do rather than what it is made of. Many hypothetical particles have been proposed, and experiments around the world have tried to detect them directly, but no candidate has yet been confirmed as the dominant dark matter of the cosmos. Some researchers therefore continue exploring whether modifications to our understanding of gravity could reproduce at least part of the evidence without invoking an unseen substance, although any successful alternative has to explain a wide range of observations at the same time, not merely the rotation of individual galaxies. That scientific tension is useful rather than embarrassing, because dark matter is not accepted simply because galaxies look like they need glue. It is inferred because many independent measurements behave as though additional gravitating mass is present. Even the phrase "holding galaxies together" should be understood carefully. Galaxies would not instantly explode if dark matter vanished in some imaginary experiment, but their present orbital speeds and structures could not be explained in the same way with the visible mass we observe. The unseen halo appears to provide much of the gravitational potential in which the luminous galaxy moves. So when you look at a spiral galaxy and admire its bright arms, you may actually be seeing only the most obvious component of a much larger system. The stars trace the part that shines. Their motions hint at the part that does not, and perhaps that is the unsettling lesson hidden in a galaxy's rotation. Sometimes the strongest evidence for what exists comes not from seeing the thing itself, but from realizing that everything visible is moving as though something unseen has been there all along. Most of the matter in the universe may be something we cannot directly see. If every star, planet, cloud of gas, grain of dust, ocean, mountain, and living body in the universe could somehow be gathered into one inventory, you would still be counting only a minority of the matter that appears to exist. This is one of the most important distinctions in modern cosmology. Ordinary matter, the kind built from atoms, seems to make up only about 1/6 of all matter, while the remaining majority behaves like something fundamentally different that we call dark matter. And there is an important detail here that often gets blurred in popular explanations. Dark matter is not thought to make up most of everything in the universe when dark energy is also included. Rather, it appears to make up most of the universe's matter. Ordinary atomic matter contributes only around 5% of the total cosmic energy budget, dark matter roughly another quarter, and the larger remaining share is associated with dark energy, which is a separate mystery connected to the accelerated expansion of space. So, how can scientists claim that invisible matter dominates the material universe when no one has directly collected a piece of it? The answer comes from several independent clues that reach far beyond the motion of individual galaxies. One of the strongest comes from the cosmic microwave background, the ancient radiation released when the universe was only about 380,000 years old. That faint glow contains tiny variations in temperature across the sky, and the statistical pattern of those variations depends on how much ordinary matter, dark matter, and other components existed in the early universe. When scientists compare those patterns with models of cosmic evolution, the amount of gravity required cannot be supplied by ordinary matter alone. There is another independent clue from the production of the lightest elements. In the first minutes after the Big Bang, the young universe was hot enough for nuclear reactions to create hydrogen, helium, and small amounts of other light elements. The measured abundances place tight limits on how much ordinary proton and neutron matter could have existed. You cannot simply hide enough normal matter in dim stars, cold planets, black clouds, or unseen debris to account for all the missing gravity, because the early universe chemistry would no longer match what we observe. Dark matter therefore appears to be genuinely different from ordinary atomic matter. Not merely ordinary material that happens to be difficult to see. Its presence also helps explain how structure formed. The early universe was remarkably smooth, with only tiny differences in density. Yet over billions of years, those differences grew into galaxies and vast clusters. Dark matter, because it does not interact strongly with light, could begin gathering gravitationally without being pushed around by radiation in the same way ordinary gas was. It effectively provided gravitational wells into which normal matter later fell, helping the first large structures develop more efficiently. What dark matter actually consists of remains unknown. It may involve a particle or family of particles that interacts only weakly with ordinary matter, and many experiments have searched for such particles without yet finding a confirmed answer. That uncertainty does not mean the evidence for missing mass disappears. It means we seem to understand the gravitational role far better than the microscopic identity. And perhaps that is what makes the problem so intellectually uncomfortable. Almost everything you have ever touched belongs to the minority component. The atoms that make your body, the planet beneath you, and every visible star are chemically rich, luminous, and familiar, yet they may represent only a small fraction of the matter shaping cosmic structure. The universe seems to be telling you that familiarity is a poor measure of importance. The material you know best may be only the visible residue of a much larger hidden architecture. Galaxy clusters can contain far more hidden mass than visible matter. Galaxy cluster can contain thousands of galaxies, enormous clouds of superheated gas, and enough visible material to seem almost unimaginably massive. Yet even after astronomers count all of that, most of the cluster's gravitational mass can still be missing from view. Galaxy clusters are the largest gravitationally bound structures in the universe, and they provide one of the clearest places to compare what shines with what actually gravitates. The first clue comes from the galaxies themselves. Individual galaxies inside a cluster move at hundreds or sometimes more than 1,000 kilometers per second, racing through a shared gravitational environment rather than orbiting one single central object. If you estimate the cluster's mass using only the light from its stars, those galaxies often appear to be moving too rapidly for the visible material to keep the system bound over cosmic time. Something else must be deepening the gravitational well, but astronomers do not rely on galaxy motions alone. Clusters also contain enormous quantities of gas filling the space between galaxies, heated to tens of millions of degrees. This gas is so hot that it shines mainly in X-rays rather than visible light, and in many clusters it contains more ordinary matter than all of the stars combined. By measuring its temperature and how pressure changes across the cluster, scientists can estimate how much gravity is required to confine it. Again, the answer comes out far larger than the mass of the stars and hot gas that can be directly accounted for. Then, there is an entirely different measurement: gravitational lensing. The cluster's total mass bends light arriving from galaxies located much farther behind it, stretching those distant sources into arcs, creating multiple images, and producing subtle distortions across the background sky. Because the amount of bending depends on total mass rather than brightness, lensing lets astronomers map the cluster's gravitational structure without needing to know what the mass is made of. The resulting maps usually show that most of the mass is distributed through a broad invisible component surrounding and extending beyond the luminous galaxies. Some of the most dramatic evidence comes from clusters that have collided with one another. In these systems, the hot ordinary gas from each cluster can slam together, slow down, and remain concentrated near the collision region because gas particles interact directly. The galaxies mostly continue onward because stars rarely collide, and gravitational lensing maps reveal that much of the total mass also moves with those galaxies, rather than staying with the slowed gas. This separation is difficult to explain if most of the mass was simply hidden ordinary gas. It behaves more like a largely collisionless component passing through the encounter with relatively little direct interaction. Exactly the broad behavior expected from dark matter. The famous examples are striking, but scientists do not base the entire case on one unusual collision. The strength comes from many clusters, examined with several independent techniques that repeatedly point toward more mass than the visible material can supply. There are still complications. Estimating cluster masses requires careful modeling. Clusters are not always perfectly relaxed systems, and researchers continue testing alternative theories of gravity. But any successful explanation has to reproduce galaxy motions, the behavior of hot gas, lensing maps, cosmic structure, and colliding clusters together. That is a far more demanding test than simply explaining one strange observation. A galaxy cluster therefore teaches you something more subtle than there is invisible stuff out there. It allows you to weigh darkness by watching how thousands of galaxies move, how million-degree gas is confined, and how background light is distorted. The hidden mass never needs to shine for its distribution to become measurable. What looks like a crowded collection of bright galaxies may actually be only the luminous skeleton inside a much larger gravitational body, reminding you that even the grandest structures you can see may be dominated by something that refuses to appear in the image at all. The universe is filled with a giant cosmic web of galaxies and dark matter. If you could step far enough away from the universe to see its largest patterns at once, galaxies would stop looking like isolated islands and begin to resemble threads woven through an enormous three-dimensional web. This structure is known as the cosmic web, and it stretches across hundreds of millions of light years, linking galaxies into long filaments, broad sheets, and dense intersections where galaxy clusters gather. The pattern did not appear because galaxies somehow chose to line themselves up after they formed. Its beginnings were already present when the universe was extremely young, when matter was distributed almost evenly, but not perfectly. Some regions contained slightly more material than average, while others contained slightly less. Those differences were tiny, yet gravity had billions of years to work on them. Denser regions attracted additional matter, becoming still denser, while material gradually flowed away from emptier regions. Over time, the small irregularities grew into a network. Matter collapsed first along one direction into broad sheets, then along another into filaments, and finally accumulated most strongly at the intersections where massive clusters could form. Dark matter plays a central role in this story because it appears to provide much of the underlying gravitational framework. Computer simulations that begin with the conditions measured in the early universe naturally produce web-like structures when dark matter and gravity are allowed to evolve, and the resulting patterns strongly resemble the distribution of galaxies mapped by real surveys. Ordinary gas follows this structure too, but not all of it ends up inside galaxies. A significant amount is thought to remain spread through the filaments themselves as extremely thin, warm or hot gas, making parts of the cosmic web difficult to detect directly. Astronomers search for this material by observing how it absorbs background light, how it emits faint radiation, and how matter between galaxies affects distant signals. The web is therefore not simply a drawing made by connecting visible galaxies with imaginary lines. The filaments contain real matter, and galaxies tend to form and evolve within this larger environment. A galaxy falling along a filament may eventually enter a cluster, while smaller systems can merge or exchange gas as they travel through the same structure. Even the directions in which galaxies spin may retain some influence from the larger flows of matter that helped assemble them. Yet the cosmic web has no central hub from which everything extends. Every sufficiently large region participates in the same statistical pattern, with dense knots connected by filaments and separated by vast underdense spaces. That scale is what makes the idea so difficult to absorb. A galaxy already contains billions of stars and can span tens of thousands of light years. But on the scale of the cosmic web, even whole galaxies become tiny markers, tracing something much larger. You begin by thinking of the universe as a collection of objects scattered through empty space. Then discover that those objects belong to a structure whose shape was slowly amplified from nearly invisible differences laid down in the earliest cosmic history. The largest architecture in nature was not built from solid beams or boundaries. It emerged because gravity patiently exaggerated tiny inequalities until they became the immense network through which galaxies still move today. There are enormous voids containing surprisingly few galaxies. The strangest places in the universe may not be where too much matter exists, but where almost nothing gathered in the first place. Between the filaments of the cosmic web lie enormous regions called cosmic voids, some stretching tens or even hundreds of millions of light years across. while containing far fewer galaxies than the cosmic average. They are not perfectly empty bubbles carved out of space, and describing them as absolute nothingness would be misleading. Voids can contain thin gas, dark matter, and occasional galaxies, but their density is dramatically lower than that of the walls and filaments surrounding them. Their origin begins with the same tiny differences that shape the rest of large-scale structure. Regions that started slightly underdense had weaker gravitational attraction than their surroundings, so matter gradually moved toward nearby denser regions instead of accumulating inside them. As material drained away, the underdense region effectively became emptier relative to everything around it. In a useful sense, voids grow with time, not because a physical wall pushes outward, but because matter continues leaving their interiors while the boundaries around them gather more material. This creates one of the more counterintuitive motions in cosmology. A galaxy near the edge of a void can appear to move away from the void's center as it is drawn toward denser structures outside, making the empty region expand in relative size. Voids also tend to merge. Smaller underdense regions can become incorporated into larger ones as the structures separating them weaken, producing immense low-density volumes bounded by sheets and filaments of galaxies. Astronomers identify these regions using large galaxy surveys that measure the three-dimensional positions of enormous numbers of galaxies. When the map is reconstructed, voids emerge not as tiny gaps between neighboring systems, but as major components of the universe's architecture. In fact, much of cosmic volume is occupied by these underdense regions, even though most galaxies and much of the matter are concentrated elsewhere. The few galaxies that do live inside voids are scientifically useful precisely because their environment is unusual. They experience fewer close encounters and mergers than galaxies in crowded clusters, allowing researchers to ask how galaxies evolve when their surroundings are comparatively quiet. Some void galaxies are small and actively forming stars, offering a contrast with populations found in denser regions. Voids also matter for cosmology because their shapes and growth respond to the overall expansion of the universe and to the way gravity organizes matter. By comparing observed voids with computer simulations, researchers can test whether a cosmological model produces the right balance between crowded structures and empty ones. Even the word empty begins to feel inadequate once you understand what these regions represent. A void is not a failure of the universe to build something. It is an expected result of structure formation, just as necessary to the pattern as the filaments that surround it. Matter concentrating somewhere means matter must become relatively scarce somewhere else. So when you picture the universe on its largest scales, do not imagine galaxies sprinkled evenly through darkness. Imagine a landscape dominated by contrast. Dense threads of galaxies surrounding enormous quiet volumes where very little ever collected. The universe formed its grandest pattern not only by deciding where matter would gather, but also by leaving behind places where almost none of it stayed. Space itself can expand faster than light without violating relativity. There is no rule in Einstein's relativity saying that the distance between two extremely remote regions of the universe must increase more slowly than light can travel. And this is where one of cosmology's most misunderstood ideas begins. You are probably familiar with the statement that nothing can move faster than light, but that limit applies locally. If a spacecraft passes you through nearby space, you will never measure it moving past you faster than light. Cosmic expansion is different because distant galaxies are not necessarily racing through one fixed, unchanging arena. On the largest scales, the geometry used to describe the universe is itself changing, so the distance between widely separated locations can increase even when neither location is locally breaking the speed limit. It is tempting to picture space as a rubber sheet being stretched, but that analogy can become misleading if you imagine a physical substance pulling galaxies apart. Space is not a material fabric with atoms hidden inside it. What changes is the scale of the geometry. As the universe expands, sufficiently distant locations become farther apart according to the way cosmic distances are defined. The larger the separation, the more expansion can accumulate between two regions, which is why very remote galaxies can have recession rates greater than the speed of light. No galaxy needs to fire an engine and accelerate through its immediate surroundings beyond light speed for this to happen. Imagine placing markers along an enormously long ruler whose intervals gradually grow. Two neighboring markers might separate very slowly, yet markers thousands of intervals apart could gain distance from each other extremely quickly, because every small increase between all the intermediate points contributes to the total separation. Cosmology works somewhat like this. Although the universe has no outside ruler and does not need to expand into another empty space. That last point is important. The Big Bang was not an explosion from one location into a pre-existing void, with galaxies flying outward from a central point. On large scales, expansion happens between distant regions everywhere, and an observer in another galaxy would see the same broad pattern of sufficiently remote galaxies receding. Relativity is built to accommodate this because Einstein's theory of gravity is not merely a theory about objects moving inside space. It describes how spacetime itself can curve and evolve. The famous light speed limit still governs every local experiment. If you stood beside a beam of light, nothing carrying matter or usable information could overtake that beam in your neighborhood. But relativity does not require the cosmological distance between you and something billions of light years away to obey the same simple rule as the speedometer of a passing spacecraft. This distinction also helps explain why saying space expands faster than light is useful but incomplete. There is no single universal expansion speed for all of space. Nearby distances increase slowly, larger distances increase faster, and whether a particular recession rate exceeds light speed depends on how distance is defined in an evolving universe. The surprising lesson is therefore not that Einstein's speed limit has an exception hidden inside it. The lesson is that you were probably applying a local rule to a global situation where the meaning of distance itself is changing. Once you separate motion through space from the changing geometry between distant places, the apparent contradiction dissolves. Light remains the ultimate local speed limit, while the universe as a whole is free to change its scale in ways that no ordinary journey across a fixed background could imitate. Some galaxies are receding from us faster than light because space is expanding. Some galaxies whose light you can detect today are now receding from us at a rate greater than the speed of light. And the strangest part is that this does not prevent us from seeing them. At first that sounds impossible. If something is moving away faster than light, you might assume that any light it sends toward you must lose the race forever. That reasoning would be correct for an object locally flying through ordinary space faster than its own photons. But cosmological recession is not that kind of motion. A distant galaxy can remain locally ordinary while the enormous amount of expanding universe between you and it causes its cosmological distance from you to increase at a superluminal rate. The light itself still travels locally at the speed of light everywhere along its journey. What changes is the geometry through which that journey takes place. This leads to a beautiful and unintuitive possibility. A photon can be emitted toward Earth from a very distant galaxy, even while the total distance between that galaxy and us is initially increasing. The photon is always moving toward us through its local surroundings, yet expansion across the vast intervening distance can, for a time, increase the remaining distance faster than the photon reduces it. As the universe evolves, however, the balance can change. The region within which light can make net progress toward us has not remained fixed throughout cosmic history, so photons that once seemed to be losing ground can later find themselves in conditions where their distance from us begins to shrink. After billions of years, some of those photons finally arrive at Earth. This is why receding faster than light does not automatically mean forever invisible. Astronomers can observe galaxies that are currently beyond the distance at which the simple present-day recession rate equals light speed, because the photons reaching us now began their journeys under different cosmic conditions. their light is also stretched during the voyage. As the universe expands, the wavelength of traveling radiation is stretched with it, shifting ancient visible or ultraviolet light toward redder and often infrared wavelengths by the time it reaches us. Measuring that cosmological redshift is one of the principal ways astronomers learn how much the universe has expanded since the light was emitted. But you should be careful with the phrase, "How fast is that galaxy moving?" For nearby objects, velocity is straightforward enough to imagine. At billions of light years, there is no single simple global speed that everyone in the universe would measure in the same way, because comparing velocities at widely separated locations in curved, evolving space-time requires a choice of cosmological coordinates. The statement that a distant galaxy is receding faster than light refers to a well-defined cosmological recession rate based on how its proper distance changes with cosmic time, not to someone standing beside that galaxy watching it blast through local space beyond the light barrier. That distinction allows something that initially feels paradoxical. We can receive ancient light from a galaxy whose present cosmological recession rate exceeds light speed. You are therefore never seeing the distant universe as it is right now in any simple universal sense. You see each galaxy through photons that departed at a particular stage of cosmic history, while the galaxy and the space between you have continued evolving during the journey. By the time the light reaches your telescope, its source can be much farther away than the straightforward light travel time might suggest. A distant galaxy can thus be both observable and presently superluminal in its recession, not because light failed to obey relativity, but because the universe changed while the light was on its way. And that leaves you with a deeper way to think about looking into space. Every distant image is not merely a picture of somewhere far away. It is the surviving end of a journey through a universe that refused to remain the same size while the message was traveling. There are parts of the universe we can see but can never reach. One of the strangest boundaries in the universe is not a wall, a force field, or an edge you could ever touch. It is a limit created by the future itself. There are galaxies whose ancient light is reaching our telescopes today, even though, under our best understanding of cosmic expansion, no spacecraft launched from Earth now could ever reach them, no matter how long it traveled, and no matter how close to the speed of light it moved. The key is that seeing something and being able to visit it are completely different problems. Light arriving today began its journey long ago, when the universe was smaller and the source was much closer in the cosmological sense. Since then, the space separating us from that region has continued to expand. For sufficiently distant places, that expansion creates what cosmologists call a cosmic event horizon, a boundary beyond which events happening now will never be able to send signals that eventually reach us, and beyond which signals we send now can never arrive. This does not mean those galaxies suddenly cease to exist, nor does it mean there is a physical curtain around our part of the cosmos. It means the changing geometry of the universe prevents any influence beginning today from crossing the growing separation. The distinction becomes clearer if you imagine two distant shores with a river between them whose current continually strengthens. A message in a bottle released long ago, when the current was weak, may still reach you today, even though a boat leaving your shore now could never make the reverse journey against the stronger flow. The analogy is imperfect because galaxies are not moving through a literal cosmic river, but it captures the unsettling asymmetry. Receiving old information does not guarantee future access. This also means the observable universe is not identical to the part of the universe we can influence. Our telescopes can show us ancient states of regions that are already, in a practical causal sense, slipping beyond our future. Over unimaginably long periods, if cosmic acceleration continues as current evidence suggests, more distant galaxies will cross beyond our ability to communicate with them. Their already emitted light may continue arriving for a while, increasingly stretched and weakened, but future events within those galaxies will never become part of our observable history. Eventually, Observers in the far future could inhabit a universe that looks dramatically emptier than ours, not because most galaxies vanished, but because their light could no longer reach the local region. This is one of the rare places where cosmology forces you to separate existence from accessibility. Something can be real, can once have been visible, can even have sent you photons that you are receiving now, and still be forever beyond any journey you could begin today. The universe, therefore, contains destinations that are not merely too far for current technology, they are excluded by the large-scale structure of space-time itself. And that changes what the night sky means. Every distant galaxy is not automatically a place waiting to be reached one day. Some are more like messages from shores that have already begun receding beyond the possibility of contact, reminding you that observation is not possession, and that the universe can reveal something to you even after the future path toward it has quietly closed. Some light reaching Earth. Today has been traveling for more than 13 billion years. There are photons entering telescopes on Earth tonight that began their journey before the Sun, the Milky Way in its present form, or even most of the galaxies you recognize today existed. Light from some of the most distant known galaxies has been traveling through the universe for more than 13 billion years, meaning that when astronomers detect it, they are not seeing those galaxies as they are now, but as they were during the universe's infancy. This is one of astronomy's most powerful and easily misunderstood facts. Distance is also a way of looking backward in time. Light does not arrive instantly, so every object you see is already part of the past. The moon appears a little more than a second old. The sun appears about 8 minutes old. Nearby stars appear years or decades in the past, push far enough into deep space, and the delay becomes billions of years until telescopes are receiving photons emitted when the first generations of galaxies were still assembling. Those ancient photons have not spent the entire journey crossing a universe of fixed size. While they traveled, the universe expanded, stretching the wavelengths of the light along with it. Radiation that originally left a young galaxy as ultraviolet or visible light can arrive today shifted deep into the infrared, which is why modern infrared telescopes are so important for studying the earliest galaxies. The amount of this stretching, called redshift, helps astronomers estimate how much the universe has expanded since the light was emitted. But there is a subtle point that prevents a common mistake. If light has traveled for more than 13 billion years, it does not mean the galaxy that emitted it is simply 13 billion light-years away today. During the photon's journey, cosmic distances changed enormously. The source can now be much farther away than the straightforward travel time suggests, because the universe kept expanding while the light was in transit. So astronomers distinguish between look-back time, how long the light has been traveling, and present-day distance, which describes how far away the source would be according to modern cosmological coordinates. These are related, but they are not the same thing. Ancient light is also fragile information. A photon may travel through intergalactic gas, pass near massive structures, have its wavelength stretched, and continue across billions of years before finally being absorbed by a detector built on Earth. Yet embedded in that small amount of energy is evidence about the object that produced it, the kinds of stars present, the elements in its gas, the rate at which it was forming stars, and sometimes the motion of material within the galaxy. By collecting enough of these photons, astronomers can reconstruct stages of cosmic history that no observer could ever visit directly. This is why the most distant telescope images are not simply pictures of faraway places. They are pieces of a chronological record. Look deeper, and you are watching younger structures. Look closer, and you see a more mature universe. The sky becomes a layered archive in which different distances correspond to different eras. And perhaps the most remarkable part is how ordinary the messenger is. The photon arriving after 13 billion years is not aged in the way a living thing ages. It does not become tired from the journey. It simply continues moving until something finally interacts with it. What has changed is everything around it. Galaxies formed, stars lived and died, planets appeared, life emerged on at least one world. and eventually a species built an instrument capable of catching that ancient light. The photon did nothing except travel, yet by surviving the journey, it allows you to see a universe that no longer exists in the form that first sent it. The universe was once filled with a hot plasma that light could not freely cross. There was a time when the universe had no transparent sky at all, because light could not travel very far before being scattered again. In the first hundreds of thousands of years after the Big Bang, the cosmos was far hotter and denser than anything around you today, filled not with stars and galaxies, but with an electrically charged plasma of atomic nuclei, free electrons, and radiation. The important word is free. Electrons had not yet settled permanently around nuclei to form stable neutral atoms because the temperature was high enough to keep knocking them apart. That changed how light behaved completely. A photon moving through this early universe constantly encountered free electrons, and those electrons scattered the radiation in new directions. Instead of crossing enormous distances in a straight journey, light repeatedly changed course, almost as though it were trying to travel through a dense, glowing fog. But this was not a fog made of droplets blocking light in the ordinary sense. The universe itself was opaque because charged particles interacted so efficiently with radiation. If you could somehow have existed there, there would have been no distant stars to look toward and no dark background between objects. Every direction would have been filled by intensely hot radiation, interacting almost continuously with the plasma around you. Yet this plasma was not completely smooth. Tiny regions were slightly denser than others, and gravity tried to compress them further, while radiation pressure resisted that compression. Those competing effects created pressure waves moving through the early cosmic material, somewhat like sound waves passing through a fluid, although the fluid here consisted of plasma and radiation filling the universe. These waves mattered because they left measurable patterns in the later distribution of matter. Then, as the universe expanded, it cooled. Eventually, the temperature dropped enough for electrons to remain bound to nuclei for long periods, producing mostly neutral hydrogen and helium. The change was dramatic, even though nothing exploded at that moment. Once most free electrons had been removed from the plasma and locked into atoms, photons suddenly had far fewer charged particles available to scatter them. Their average journey between interactions became enormously longer, and the universe changed from opaque to transparent. Light that had previously been trapped in an almost endless sequence of scatterings could finally travel freely across cosmic distances. This transition is often called recombination, although the name can sound strange, because it was effectively the first long-lasting combination of electrons with nuclei, not a reunion after some previous atomic era. It occurred roughly 380,000 years after the Big Bang, astonishingly early compared with the universe's current age of about 13.8 billion years. And there is a deeper consequence hidden inside that change. You might think that with a powerful enough telescope, you could simply look farther and farther back until you watched the Big Bang itself. But ordinary light reaches a natural visual barrier. Before the universe became transparent, photons could not carry a clean image across space because they were constantly scattered. Looking farther back using electromagnetic radiation eventually brings you to a kind of cosmic photosphere, the earliest period from which freely traveling light can reach us directly. What lies earlier must be investigated through other evidence, such as the behavior of particles, gravitational effects, nuclear abundances, and theoretical predictions. The early universe was therefore not darkness waiting for the first lamp to be switched on. It was almost the opposite, a universe saturated with radiation but unable to preserve a clear view across itself. Only after expansion cooled the plasma enough for stable atoms to form did space become transparent in the way you now take for granted. Every time you look through a clear night sky, you are living in a cosmic condition that did not always exist. Transparency itself has a history, and for the first long chapter of the universe, light was everywhere, but could hardly go anywhere. We can still detect radiation left over from the universe's infancy. Turn a sensitive microwave detector to toward what appears to be empty sky, and it will encounter a faint glow coming from almost every direction. A surviving relic from a time when the universe had not yet formed a single mature galaxy like the ones you know today. This radiation is called the cosmic microwave background, and it is one of the strongest pieces of observational evidence we possess about the early universe. It was not produced by stars, and it does not come from one distant location. It fills space itself, reaching Earth from every direction, because the event that released it occurred throughout the young universe. Today its temperature is only about 2.7 degrees above absolute zero, making it extraordinarily cold radiation. But it did not begin that way. Over cosmic history, the expansion of the universe stretched its wavelengths enormously. Radiation that once belonged to a much hotter environment has been shifted into the microwave part of the spectrum. So what arrives at modern detectors is a cooled and stretched version of an ancient cosmic glow. When astronomers first measured it precisely, they found that its spectrum matches that of an almost perfect thermal radiator with extraordinary accuracy. That matters because a thermal spectrum is exactly what you would expect from radiation that once spent a long period repeatedly interacting with hot matter until the two reached near equilibrium. But the cosmic microwave background becomes even more valuable when you stop looking at its average temperature and examine the tiny differences from one direction to another. The sky is not perfectly uniform. Some regions are warmer or cooler than average by only a few parts in 100,000. Differences so small that they would be invisible without extremely sensitive instruments. Yet those tiny variations are enormously important because they trace slight differences in the density and motion of the young universe. Regions that were only marginally denser eventually had billions of years for gravity to amplify those differences, helping produce the galaxies, clusters, and larger structures that appeared later. In this sense, maps of the microwave background are not photographs of finished cosmic objects. They are closer to an early blueprint, showing the faint beginnings of structures that had not yet formed. The pattern also contains information about much more than future galaxies. The sizes and strengths of the temperature variations allow cosmologists to estimate the universe's age, overall geometry, amount of ordinary matter, amount of dark matter, and several other basic properties. The radiation is also polarized, meaning its light waves have subtle preferred orientations created by interactions in the early universe. Measuring that polarization provides another layer of evidence about conditions during those ancient epochs and helps researchers separate different physical processes that shape the signal. Space missions have mapped this background across essentially the entire sky, progressively improving the precision with which those tiny patterns are measured. And yet there is an important limitation. The microwave background is not literally an image of the Big Bang at the instant the universe began. It shows us the universe at a much later but still extremely early stage, around 380,000 years after the beginning of cosmic expansion, when radiation was finally able to travel long distances without being constantly scattered. Everything before that moment is hidden from ordinary electromagnetic observation by the earlier opacity of the universe. So when you detect the cosmic microwave background, you are looking as far back with light as nature allows. The photons arriving at a detector today have spent almost the entire history of the cosmos in transit. While stars formed, galaxies assembled, planets appeared, and eventually, observers developed technology capable of recognizing what those photons represented. Their existence turns the empty sky into an archive. Even where your eyes see nothing, the universe is carrying an ancient signal from its own childhood. And the tiny variations inside that signal helped become the enormous structures surrounding you now. What appears to be faint background noise is actually one of the oldest readable pages in cosmic history. Tiny fluctuations in the early universe eventually grew into galaxies. Every galaxy you have ever seen may trace its ancestry back to an irregularity so small that, in the young universe, it would have been almost impossible to notice. Shortly after the beginning of cosmic history, matter was distributed with remarkable uniformity, but not perfect uniformity. Some regions contained slightly more material than their surroundings, while others contained slightly less, and those tiny differences became the starting points from which gravity slowly built structure. A region with a little extra mass exerted a slightly stronger gravitational pull, so over time it attracted more material. That additional matter strengthened its gravity further, allowing it to collect still more, creating a gradual amplification that continued as the universe expanded. The process was not fast. For a long period, the differences remained modest, and ordinary gas could not simply collapse instantly into stars. Dark matter was especially important because it could begin gathering into gravitational concentrations without interacting strongly with radiation or losing energy in the same way ordinary gas did. These growing dark matter halos created gravitational wells into which hydrogen and helium could later fall. As gas accumulated inside them, it became denser, and compression raised its temperature. For a cloud to continue collapsing, however, it also had to lose some of that heat. In the earliest environments, when heavy elements had not yet been produced by stars, cooling was more difficult than it would become later. Eventually, certain clouds became dense enough for molecules and atomic processes to remove sufficient energy, allowing the first stars to ignite. Those stars were probably very different from most stars forming around you today, because they were born from almost pure hydrogen and helium. They began changing their surroundings through radiation and by producing heavier elements, preparing later gas clouds for more efficient cooling and more complicated generations of star formation. Small collections of stars and gas then assembled into early galaxies, while those galaxies continued gaining material and interacting with neighboring systems. Growth therefore happened in stages. A tiny early excess of matter did not immediately turn into a spiral galaxy with billions of stars. It first became a slightly stronger gravitational attraction, then a dark matter concentration, then a place where gas could collect, then a site where stars could appear, and eventually part of a larger galactic system shaped by mergers, inflows, stellar feedback, and billions of years of evolution. This sequence also explains why galaxies are not sprinkled randomly through the universe. Their locations reflect the ancient distribution of those initial density differences, amplified and reorganized by gravity over cosmic time. What makes this story so remarkable is the contrast between beginning and result. The difference between a region destined to become unusually crowded and one destined to remain relatively empty was once incredibly subtle. Yet gravity never needed the original imbalance to be large. It needed only time. That is one of the quiet powers of gravity. It can take an almost insignificant advantage and reinforce it for billions of years until the outcome no longer looks small at all. A galaxy containing hundreds of billions of stars can therefore be understood not as something that appeared fully formed, but as the distant consequence of a barely noticeable excess of matter in the young universe. And perhaps that is the most revealing way to think about cosmic structure. The universe did not begin with galaxies waiting to be assembled from obvious pieces. It began nearly smooth with only faint imperfections, and those imperfections were enough. The largest structures in the universe began from almost imperceptible differences in density. The largest patterns in existence began with differences so slight that if the early universe had been only a little more uniform, the cosmos around you might look radically emptier today. In the leading cosmological picture, the primordial variations in density were typically only around 1 part in 100,000 at the stage we can observe them most directly. Yet those tiny contrasts contained a range of different physical scales. Some fluctuations extended across relatively small regions, while others stretched across distances that would eventually correspond to enormous cosmic structures. Gravity then treated each excess of matter as an opportunity. Slightly overdense regions resisted cosmic expansion a little more effectively than their surroundings, gradually drawing matter inward, while underdense regions lost material to neighboring concentrations. The result was not simply that isolated clumps became larger. Structure developed hierarchically, Smaller gravitationally bound systems formed, combined, fell into larger environments, and contributed to structures whose dimensions eventually reached tens or hundreds of millions of light-years. But the pattern could not grow arbitrarily. The universe was expanding at the same time, and the competition between gravitational attraction and expansion determined how quickly different regions could develop. Dark matter provided much of the gravitational framework. Ordinary matter supplied the gas from which stars and visible galaxies would later form, and the changing expansion history influenced how efficiently structure could continue growing. Scientists can study this process statistically, rather than needing to trace every individual galaxy backward. The early density variations had a measurable distribution of strengths across different scales, often described as a spectrum of fluctuations. Modern surveys then measure how galaxies are arranged across enormous volumes of space, and compare that arrangement with computer simulations that begin from early conditions. When the same basic physics evolves those faint initial variations forward for billions of years, it produces a universe with dense concentrations, elongated structures, broad low-density regions, and clustering patterns strikingly similar to what astronomers observe. This agreement is important because the universe's large-scale organization is not something inserted into the model afterward. It emerges from the initial conditions. The largest known structures are therefore not giant objects in the same sense as a star or planet, with a hard boundary holding everything together. Many are statistical arrangements of clusters and galaxies spread across immense distances, and some extremely large named structures can be difficult to define precisely because their components are not necessarily bound into one future object. That distinction prevents the idea from becoming exaggerated. Gravity has built enormous patterns, but not every apparent chain of galaxies is one single coherent structure destined to collapse together. What is scientifically secure is the broader fact that the clustering of matter today retains information about very small irregularities in the early universe. The remarkable part is how much consequence can emerge from so little difference. A barely denser patch became more attractive to surrounding matter. That slight advantage grew. Neighboring regions developed their own histories, and after billions of years, the contrast became powerful enough to organize galaxies across distances your mind can barely picture. You live inside the late-stage result of that amplification. The sky looks complicated now. Clusters, galaxies, stars, planets. But its deepest large-scale pattern began with something much simpler. A universe that was almost perfectly even, but not quite. And in cosmology, that tiny phrase, "not quite," is enough to explain why there is structure around you at all.